Imagine, if you will, standing at the fore of a technological revolution, where machines learn and innovate alongside humans. Picture yourself as the architect behind these intelligent systems, shaping the future of industries from healthcare to finance, from autonomous vehicles to space exploration. No, this isn't science fiction. It's the reality of AI and machine learning, and you're about to embark on a journey to master it. Welcome to the AI ML Engineering Advanced Professional Certificate Program. Whether you're just starting your journey into AI ML or looking to deepen your expertise, this program is designed to equip you with the skills you need to excel in the world of artificial intelligence and machine learning. In this video, you'll learn what to expect from this program, how the program is structured, and which skills you'll walk away with upon completion of the program. This comprehensive program covers the full spectrum of AI ML engineering, from foundational concepts all the way to advanced techniques. You'll dive deep into essential areas like supervised and unsupervised learning, deep learning, reinforcement learning, and AI model deployment. But that's not all. We also cover real-world applications, so you'll gain practical skills you can immediately put to use. The program is structured to provide a balance between theory and hands-on experience. You'll not only learn how algorithms work, but you'll also get plenty of opportunities to practice building, training, and deploying models. Each module includes projects and labs that are designed to simulate real-world business challenges, giving you the chance to apply your skills in meaningful ways. AI and machine learning are transforming industries around the world, and the demand for AI ML engineers is skyrocketing. From healthcare and finance to retail and autonomous systems, AI is reshaping how we work, interact, and make decisions. With this certificate, you'll be well prepared to take advantage of these growing opportunities and become a key player in this evolving, exciting field. By the end of this program, you'll have developed a solid portfolio showcasing your AI ML expertise. You'll know how to build and deploy machine learning models, fine-tune deep learning networks, and create end-to-end AI solutions that are both scalable and efficient. Whether you're aiming for a role as an AI engineer, data scientist, or ML researcher, this certificate will give you the tools and confidence to take your career to the next level. The future of AI and machine learning is unfolding right now, and you have the opportunity to be at its fore. So here's our challenge to you. Take the initial step of your learning journey by completing the first lesson of this course today. Then commit to regular learning sessions each week. We're excited to have you on board, and we can't wait to see the incredible projects you'll build throughout this journey. Thank you, and welcome again to the AI ML Engineering Advanced Professional Certificate Program. Imagine working in a hospital where early detection of disease could mean the difference between life and death. With the right AI tools, you could analyze patient data in real time, catching critical patterns early on. In this course, we'll dive into how Microsoft Azure's powerful AI and ML capabilities are making life-saving applications like these a reality and changing the face of industries worldwide. By the end of this video, you'll be able to configure and manage Azure resources for AI ML projects, implement end-to-end ML pipelines using Azure services, deploy and monitor ML models in Azure production environments, and troubleshoot common issues in Azure AI ML workflows. The Azure for AI ML course has been designed for aspiring professionals who want to delve into how Microsoft Azure can empower their artificial intelligence and machine learning projects. We'll start with a total overview of Azure's capabilities, a 1,000-foot perspective, if you will, to help you understand the vast landscape of services available. We'll also discuss the motivations that have driven some of the most successful companies to adopt Azure, and how those motivations translate into real-world impacts. Azure isn't just a platform, it's an ecosystem. Imagine a world where your AI models are developed, deployed, and managed in a seamless and highly scalable environment. Well, that's what Azure offers. From pre-built cognitive services to infrastructure for custom ML models, this ecosystem provides the tools you need to innovate without limitation. Whether you're exploring conversational AI, natural language processing, or image recognition, Azure's robust infrastructure provides all the necessary components for you to succeed. You'll come to understand why enterprises choose Azure to solve their most pressing AI challenges, and how you can utilize it to deploy models efficiently, securely, and reliably. Think about healthcare systems that need to analyze massive amounts of data to detect early signs of disease. With Azure's tools, hospitals can build and deploy machine learning models that analyze patient data in real time, leading to more accurate diagnoses and ultimately saving lives. We'll see how this kind of application is possible and how Azure is a crucial part of making it happen. In this video, we introduced Microsoft Azure and how it's revolutionizing industries with its AI and ML capabilities. You were introduced to a wide range of Azure services, from pre-built cognitive tools to infrastructure for custom ML models that provide seamless, scalable environments for developing, deploying, and managing AI applications. We also discussed the real-world impact of Azure solutions, such as enabling healthcare systems to perform real-time data analysis for early disease detection, ultimately contributing to life-saving diagnoses. Now that we've explored what's possible with Azure for AI and ML, take a moment and reflect on how these services might change the way your projects are executed. As we continue through the course, you'll get hands-on experience that will transform your ideas into reality. Get ready to take your AI, ML skills to the next level with Azure.
Think of Git as your project's safety net. It keeps track of every change, every addition, and even every mistake, allowing you to go back in time or collaborate seamlessly with others. In this video, we're going to show you how to set up a Git repository for your machine learning project so you can code with confidence and keep everything under control. By the end of this video, you'll be able to create and set up a Git repository for your project, and organize your files and structure your repository. Let's begin by initializing a Git repository for the project. Let's go to Notebooks, and let's create a new folder where the Git repository can live. I'll create a new folder, and I will name it Git Test. You can name the folder whatever you'd like. Now within Git Test, I'll right-click and create a new file. I'll call it untitled.ipynb, leave it as is, and create the new Jupyter notebook. Let's add a line here. And then save the file using Control-S. Now, let's click on the menu at the top left of the notebook panel. Then click Compute, then click Open Terminal. This option will be grayed out for you if your compute instance is not active. In that case, make sure to start your compute instance, wait for it to finish starting, and come back to this menu. Now, within the folder we've just created, run the command git init, I-N-I-T, and press enter. By initializing our repository, we can now track changes and create a history of the development process, making it easy to collaborate and revert changes if needed. Now, let's stage our files for commit and make our first commit with a meaningful message. Committing code is a crucial part of version control. First, we will stage all files in this folder using git add space period, and then press enter. You may get an error message calling out dubious ownership. This is because our directory does not exist on the compute instance itself, but elsewhere in Azure, and is simply mounted to our compute instance. Run the command listed below to add an exception, then run git add period again. I will copy the command using Control-C, then press Control-V and enter to run the command. Then I will press the up arrow twice to bring up the git add command that I ran earlier and press enter. Now, let's commit the staged files with a clear descriptive message using git commit -m. I will say git commit -m and then in quotes initial commit, and then press enter. If this is your first time using Git on this compute instance, or you don't have Git set up globally, you'll need to configure your email address and name. Do so using the provided commands, then run git commit again. I'll copy the first command using Control-C and Control-V to paste it. Before I press enter though, I will replace it with my email and then press enter. I will do the same for my name. Now that I've configured my email and name, I will try to commit the message again. And this time my commit goes through. In this video, you've set up and managed a Git repository for your machine learning project. You saw how to initialize a repository, organize files into a clean structure, and commit changes. Now it's time to put this knowledge into action. Create a Git repository for your own machine learning project, organize your files, and commit changes. Imagine losing hours of work because a bug you can't track down overwrote crucial code, or worse, because you accidentally deleted it. In this video, I'll show you how to go from local commit to full remote setup on GitHub, all the way to setting up branches for safe, efficient development. Let's dive in and make sure your hard work is protected and versioned right from the start. By the end of this video, you'll be able to commit your code with meaningful messages, push your repository to GitHub, and set up branches for effective version control in collaborative and ongoing development. Committing your code with meaningful messages ensures that every change you make is recorded, making it easier to track progress and roll back if necessary. Once we've committed the changes locally, it's time to push the repository to a remote platform such as GitHub. This makes your code accessible and backed up in the cloud. We'll create a new repository on GitHub using their web interface. Open a new tab and go to github.com and sign in or sign up for a new account. I'll create a new repository with the same name as my directory in Azure. I'll call it git test. You can use a different name, but using the same name simplifies things. Then I will click Create a new repository, making sure to keep it private. Then I will click HTTPS here and copy this URL. I will go back to my terminal and type git remote add origin space and then paste the URL I just copied. Now we need to authenticate with GitHub. Visit this link. The link will be provided for you to access the script to set up the GitHub CLI. I've copied this link and I'm pasting it in a new tab. You can also pause the video here to copy the link manually, to type the link out manually in your web browser and visit it. Here, I will copy the install script for Linux, since our compute instance runs Linux, and paste it in the terminal, then press enter to run it. When the script finishes, I will type gh space auth space login and then press enter. I will select github.com. GitHub.com is already selected, so I will press enter. I want to connect over HTTPS, so I will press enter. And I want to log in with a web browser, so I will press enter. Now, let's click this link to open the GitHub Authentication in a new tab. I will continue to sign in as Coursera AIML. I will continue to sign in to my GitHub account. Then I will go back to the terminal and copy the one-time code to paste into my web browser. Then I will click Continue. Then I will click Authorize GitHub. I will re-enter my password to confirm. And now my device is connected. Back in the terminal, I will press Enter, which will attempt to open the link in a web browser, but since there is no web browser on this compute instance, the attempt to open the browser will fail. However, the attempt to authenticate will succeed, and we have now logged in as Coursera AIML to our GitHub account. Now we will push the code to GitHub using git space push space dash u space origin space master, making sure to spell origin correctly, and then press enter. Finally, we'll set up version control for ongoing development using branches. Branching allows us to work on new features without affecting the main codebase until changes are ready. Check out a new branch for development using git checkout -b. Make sure that you have supplied a name for your new branch. Let's call this feature-branch. And then press enter. Now, let's make some changes to our Jupyter notebook. Let's say Git is a very useful tool. And then press Ctrl S to save our notebook. Returning to the terminal, we will do git space add space dot to add any new files that may have been created. Then we will type git commit space -m space and then our commit message, which in this case will be added details on Git to the Jupyter notebook, and close with a quote and press enter. Now, we will return to the master branch using git checkout master, and then merge our branch using git space merge space feature dash branch, and then press enter. Using branches allows for parallel development. You can test new features, fix bugs, or make updates without affecting the stable version of the project until everything is ready. In this video, we covered the basics of using Git and GitHub to manage and protect your code. You learned how to commit with clear messages, push your work to a new GitHub repository, and set up branches for safe, organized development. Now, you have the tools to track changes, collaborate, and ensure a stable project. Try it yourself. Set up a GitHub repo, commit with clear messages, and create a branch for new features. Imagine you're a data scientist ready to train a powerful model that could transform how your company predicts customer behavior. But first, you need the right resources to get started. In this video, we'll show you how to configure a compute instance and execute code in Azure Machine Learning. Two critical resources that will empower you to bring AI-driven insights to life in real-world projects. By the end of this video, you'll be able to navigate the Azure Machine Learning workspace to set up essential resources, create a compute instance to run machine learning experiments, and run Python code in Azure ML. The first step is to create an Azure account. If you don't already have an Azure account, visit the Azure portal at portal.azure.com in your web browser and press enter. Here, if you haven't already been signed in, you will be prompted to sign up for a free account. Your free account will include a $200 credit that expires after 30 days. If you do not complete this program within 30 days, you'll need to upgrade to a pay-as-you-go account to complete the program. Also note that students at eligible institutions may be eligible for a $100 credit that expires after 12 months. I've already created an Azure account and signed in with it, so let's go to the Azure Machine Learning Studio at ml.azure.com. If this is your first time visiting, Azure may prompt you to sign in to create a new workspace. If it does not, click Create Workspace near the top right. Let's give our new workspace a name. I will call it Test Workspace 2. Optionally, choose a friendly name. I'd recommend that your friendly name be identical to your workspace's proper name. We will use Azure Subscription 1 and the default resource group. You may be prompted to create a resource group. If so, click Create New and follow the prompts. Then, select the region that is geographically closest to you, and then click Create. It may take a few minutes for Azure to create your workspace. Now that Azure has successfully created our workspace, I will click on it to enter the workspace. In the left panel, under the Authoring section, is Notebooks. Click on Notebooks. In the Notebooks section, click Create Compute. This will create a compute instance. A compute instance is a virtual machine on which Azure ML will run the code that comprises your machine learning models. Give your compute instance a name. I'll choose the name Test Workspace 2 Instance 1. I'll select CPU as the virtual machine type and leave the virtual machine size at its recommended value. This should have sufficient resources for your virtual machine for your machine learning tasks. Now click Review and Create, and then click Create. It may take some time for your compute instance to finish creation. To see progress on the creation task, you can go to Manage, scroll down in the left tab, go to Manage, and then go to Compute. And you can see your compute instance being created. In the meantime, let's create a Jupyter notebook. Go back to Authoring and then Notebooks, and then click the plus icon, that is the Add Files button, and then Create New File. Let's change the name of this new file to test.jpg. .ipynb, that is a Jupyter Notebooks file, and then click Create. If you just created your first compute instance, you'll have to wait for Azure to finish creating it before you can proceed to the next step. This can take some time. All right, we can see now that our compute instance has finished creating. It is now running and has automatically attached to our Jupyter Notebook. I will close the File Explorer to give a better view of the Jupyter Notebooks panel. If your compute instance doesn't automatically attach, you can select it here from the drop-down menu. Now, the kernel selection menu is on the top right. Click on it, and then click Python 3.8-Azure ML, or the latest version of the Azure ML kernel. It'll take a moment to become active. Now, type this code into the code cell in your notebook. I will copy and paste it. It will be made available to you to copy and paste also. Then press Shift-Enter to run the code and proceed to the next code cell. What this code does is import the TensorFlow library as the name TF. Then it prints TensorFlow version, :space, and then TF.__version__. Note the two underscores on either side of version. When using libraries like TensorFlow, you will get error messages you can safely ignore because they pertain to GPU functionality and you're using a CPU-only compute instance. Generally speaking, when working with Jupyter Notebooks, if you see an error message that has CUDA in it somewhere, CUDA, you can safely ignore it. Here, we can see our TensorFlow version is 2.17.0. Also note that modifications in code cells don't immediately take effect. If you change code in a previous cell, it's recommended to click the Restart Kernel and Run All Cells button. Also note that new notebooks will use the Python 3.10 SDKv2 kernel by default. Make sure you change your kernel to Python 3.8-Azure ML or the latest version of the Azure ML kernel. In this video, you learned the foundational steps for configuring resources in Azure Machine Learning. Starting with the Azure ML workspace, you navigated key features and familiarized yourself with the tools available for setting up resources. You then created a compute instance, understanding how to select the right VM size based on project needs. Following this, you ran Python code in a Jupyter Notebook on your new compute instance. Now, take a moment to practice these configurations in your own Azure ML workspace. Set up a compute instance and run Python code to solidify your learning. With hands-on experience, you'll be ready to manage essential resources in any machine learning project using Azure Machine Learning.
In industries like healthcare, finance, and even aviation, companies rely on Azure Machine Learning to centralize their AI projects, creating streamlined, efficient workflows. Let's start your journey by setting up your own Azure ML workspace, a tool that consolidates your data, models, and resources, enabling smoother collaboration and more effective management of your machine learning operations. In this video, we provide an introduction to setting up Azure Machine Learning workspaces, the foundation for managing AI ML projects in Azure. The Azure ML workspace serves as the hub for organizing resources, managing experiments, and deploying models, making collaboration and resource management efficient. By the end of this video, you'll be able to explain what an Azure Machine Learning workspace is and its importance. You'll recognize the key components of an Azure ML workspace, and you'll be able to describe how a centralized workspace can streamline AI ML projects. An Azure ML workspace centralizes experiments, datasets, compute targets, and models. It provides the infrastructure for developing, training, and deploying machine learning models, enabling teams to work together cohesively. Key components include compute resources, data stores, data sets, experiments, and pipelines. Compute resources provide scalable virtual machines and clusters for training jobs, while data stores manage and store data. Experiments and pipelines help track model iterations and automate workflows. The workspace provides a standardized environment for machine learning projects, ensuring consistency and simplifying collaboration with stakeholders. It also streamlines resource management and cost tracking, leading to more efficient workflows. Visualized for you now is a depiction of a streamlined, centralized workflow using AI ML operations in an Azure ML workspace, leading to improved efficiency in data processing, model training, and deployment, in this example, within the airline industry. In this video, you learned about setting up an Azure Machine Learning workspace, a foundational tool that centralizes all essential resources for managing AI and ML projects. The Azure ML workspace organizes compute resources, data sets, models, and experiments into a single hub, enabling efficient collaboration, resource management, and ultimately cost tracking. You explored the core components of the workspace, including compute resources, data stores and sets, experiments, and pipelines. And you also understood how it streamlines workflows across various industries such as healthcare, finance, or our example, aviation. Now, take the next step in your machine learning journey by setting up your own Azure ML workspace. Familiarize yourself with its components and begin exploring the benefits of a centralized environment for your AI projects. Stay tuned for upcoming videos that will guide you through configuring resources and managing experiments in Azure Machine Learning.
Picture this. You've just wrapped up a brilliant machine learning model, but when your colleague tries to replicate your results, chaos ensues. Missing files, incomplete libraries, and unclear instructions. Let's avoid that nightmare. In this walkthrough, we'll show you how to create a workspace that's not only organized, but also collaboration ready. By the end of this video, you'll be able to establish a structured workspace, implement version control, and configure Jupyter and follow best practices. Start by going to ml.azure.com in a web browser and signing in if prompted. For this demonstration, I've already created a new workspace and compute instance. You can review previous lessons for help with creating a new workspace and compute instance. I will click on my workspace to enter it, and then scroll down in the left panel to Manage and then Compute, and make sure that my compute instance is running. Let's start by creating a structured directory for our project. A consistent and logical file structure helps keep your work organized. Let's go to Authoring and then Notebooks. Then let's click the plus icon for Add Files and click Create New Folder. The first folder will be called Data. This folder will contain raw data and processed data files. Then create a folder and name it Notebooks. Place all Jupyter notebooks here for data exploration and prototyping. Then click Create New Folder and call it Scripts. This is where Python scripts for data preprocessing, model training, and evaluation should go, or at least any preprocessing, training, or evaluation that isn't done in a Jupyter notebook. Click Create. Then, create a new folder and name it Models. Use this directory to store trained models and their versions. Click Create. Finally, click Add Files, create new folder, and name it logs. Store logs that track the execution and performance of your scripts here. Next, set up your virtual environment. A virtual environment is crucial to manage dependencies and avoid conflicts between projects. Use Conda to create a virtual environment for your machine learning workspace. Click on the terminal icon here, Open Terminal. Then collapse the File Explorer to make the terminal larger and easier to use. First, type this command and then press Enter. It will be made available to you to copy and paste. This command uses Conda to create a new virtual environment with the name new_ml_env. When prompted, press Y and then press Enter. Now Conda has created a new environment named new_ml_env. Now activate the environment by copying this command here and pasting it, and then press Enter. This command will also be made available to you to copy and paste. Now we are in our new virtual environment. You can see here at the beginning of the terminal, new_ml_env is the active environment. A virtual environment helps keep project dependencies isolated, ensuring that different versions of packages do not interfere with each other. This is especially important for machine learning projects that rely on specific versions of frameworks. Once the virtual environment is set up, install the necessary packages. It's a good idea to use a requirements.txt file to ensure that all collaborators are using the same versions of packages. Copy this code and paste it into your terminal. It will run automatically. This code will also be made available to you to copy and paste. Here, we will create a file called requirements.txt and put the lines pandas, scikit-learn, matplotlib, and tensorflow in it. And then it is saved to a file called requirements.txt. Then we use conda install --file requirements.txt to automatically install the packages we defined in requirements.txt. Conda will ask us if we want to proceed. Press Y and then Enter when prompted. Using a requirements.txt file ensures that anyone working on the project can easily replicate the environment by installing the exact dependencies needed for the project. Let's wait until Conda finishes configuring all of the packages we just downloaded. This may take a while. Set up version control next. Use Git to track changes in your project. Version control is essential for maintaining a history of changes, facilitating collaboration, and avoiding accidental data loss. For detailed instructions on setting up version control, see the screencasts in Module 1 on creating a code repository. Version control helps track the history of your files, revert to earlier versions if needed, and collaborate with others effectively. This ensures that all changes are documented and recoverable. The next step is to configure Jupyter Notebooks. Jupyter Notebooks are great for prototyping and data exploration. Configure Jupyter to use your virtual environment as its kernel to avoid conflicts. First, have Conda install Jupyter. I'm going to copy and paste this code into my terminal. It will also be made available to you to copy and paste. Paste it and then press Enter. Press Y when prompted, then press Enter. Now that Conda has successfully installed Jupyter, we will add the virtual environment to Jupyter as a kernel. I will copy and paste this code. It will also be made available to you to copy and paste. We will run pip install ipykernel and then python-m ipykernel install /user --name, the name of our new virtual environment. You should change this if you used a different one. And then display name, ML project env. And now we see that IPY kernel has installed a new kernel named ML project env. This setup ensures that your notebooks are using the correct dependencies specified in your virtual environment, preventing issues related to conflicting package versions. Now, let's open a new Jupyter notebook, select the compute instance, and observe that your new virtual environment is visible. To do this, open the File Explorer, click Add Files, click Create New File, make sure the file is of a type Jupyter Notebook, and then click Create. Close the message, collapse the File Explorer, make sure you're attached to the compute instance you are using the terminal in, and then click on the kernel selection panel. You should be able to see the new kernel you defined. The next step is documentation. Keep a readme.md file in your workspace to describe the project, dependencies, and setup instructions. This will help anyone new to the project get started quickly. To do this, expand the File Explorer, then click Add Files, then click Create New File, and name it readme.md. This is of file type Other, and then click Create. Let's edit it with the Markdown editor icon near the top left. Let's also collapse the File Explorer to make our actions better visible. I will type some text here, and then click Save, and then click Markdown Preview to view our readme.md file. A well-organized workspace setup is crucial for efficient and effective machine learning development. With a structured directory, isolated dependencies, version control, and proper documentation, you'll have all the tools needed to streamline your workflow. This setup not only makes your work more manageable, but also helps in collaborating with others more effectively. Feel free to revisit this walkthrough as you set up your own workspace, and remember, a clean workspace is the foundation for successful machine learning projects.
Imagine you're building a machine learning model that analyzes massive volumes of healthcare data to predict patient outcomes. But where do you store these data types, and how do you access them efficiently? Today, we'll walk you through Azure's diverse storage options and show you how to choose the best ones to keep your machine learning projects on track from start to finish. By the end of this video, you'll be able to explain the different data storage solutions available in Azure for machine learning projects. You'll be able to describe how each of these storage solutions fits different data requirements and use cases. You'll be able to identify the benefits of choosing the appropriate storage solution for optimizing machine learning workflows. In this video, we introduce data storage solutions for Azure Machine Learning projects, and we'll explain how these different storage options will fit into the larger context of machine learning. After all, data is the foundation of any AI or ML project, and selecting the right storage solution is crucial for efficiency and scalability. Azure provides a range of services that can be tailored to various data types and requirements, helping optimize performance, minimize cost, and ensure compliance. Let's consider a healthcare company aiming to implement machine learning for patient outcome prediction and operational efficiency. Azure Blob Storage is used to store large volumes of unstructured data, such as medical images and sensor data from devices, which can then be used for training future models. Azure Data Lake Storage helps handle both structured patient records and unstructured clinical notes, providing a single platform for data processing and analysis. For structured data, Azure SQL database is ideal for storing patient demographics and appointment history, making it easy to perform relational queries. Azure Cosmos DB can support real-time analytics by storing fast-changing patient metrics like vital signs, including heart rate or O2 sat, amongst others, allowing for quick response in emergency scenarios. Lastly, Azure File Storage enables secure sharing of model artifacts and logs across different teams working on the project. In summary, this video covered Azure's various data storage solutions, including blob storage, data lake storage, SQL database, Cosmos DB, and file storage. We discussed the specific use cases of different storage solutions and how each can be effectively deployed in a healthcare setting. In some cases, multiple storage solutions may be used together to meet specific requirements. For example, a SQL database could manage file details and locations for a patient's imaging data stored in blob storage, while a data lake holds the patient's medical history. By carefully selecting the appropriate storage solution or combining solutions as needed based on the use case, you can optimize efficiency, scalability, and security for your machine learning projects. Take the next step by incorporating one of these Azure storage solutions into your own machine learning workflows and consider how it can streamline data management for your specific use case.
In the world of machine learning, data is your foundation, and having the right storage solution can make or break your project. Azure's storage options aren't just about storing data. They're about streamlining workflows, scaling seamlessly, and ensuring security. Join us in this video to see how these solutions can transform your approach to managing data for AI and ML projects. In this screencast, we will walk you through the different ways to store and process data in Azure Machine Learning Studio. We will cover the essential configurations and provide insights into best practices for each solution, ensuring that your data management is both efficient and scalable. By now, you should know the importance of selecting the right data storage solution for machine learning projects. By the end of this video, you'll be able to explain data assets, data stores, dataset monitors, data importing in Azure ML Studio, and data connections in Azure ML Studio. First, go to ml.azure.com and sign in if needed. Open your workspace by clicking on it, and then go to Assets and then Data. Click on Data. Your screen may differ from mine depending on which courses you've completed. The first tab here shows Data Assets. As described here, data assets are immutable references to your data that can be created from data stores, local files, public URLs, or open datasets. Data assets created with Azure ML v2 APIs cannot be deleted, but you can upversion or archive them for easy referencing and reuse in machine learning tasks. Deleting data assets created with v1 APIs will permanently delete the data asset and all metadata. For reference, throughout this course and other courses, you've mostly, if not exclusively, been using the v1 API. Next, let's look at data stores. Data stores securely connect to a storage service on Azure by storing connection information. With data stores, you no longer need to provide credential information in your scripts to access your data. Data stores provide a more secure and convenient way to store data in Azure ML Studio. When you create a new workspace, a few default data stores are created. The Workspace Working Directory data store, here, I will click on it to show you, stores your working directory, all of your Jupyter notebooks and their associated files. If you click here and go to Users, you can see Coursera AIML and all of the files that have been created so far in these screencasts. Going back to data, Workspace Blob Store, here, is used by Azure ML to store data related to your ML jobs. Here you can see data related to jobs we've submitted to Azure ML for training or inference. Next, let's look at dataset monitors. This feature is in preview, but some of the associated technologies have been deprecated, and dataset monitors may be removed in the future. Using this feature requires first enabling model data collection, but Microsoft's documents indicate that this feature has been deprecated. You can learn more about that by clicking here on Learn More. When active, Dataset Monitors tries to detect data drift between a model's dataset and its inference data. Next, Data Import. Data import jobs can be run once or in a schedule, and import data from external storage services into Azure ML. For example, click Add Import and see the options. You can import data from Snowflake, Azure SQL, drawing data from elsewhere within Azure, or from S3, a component of Amazon Web Services, or AWS, and possibly the most popular cloud storage solution. Data imported from these sources can be processed and used in training tasks. I'll click Cancel. And finally, click on Data Connections. Data connections are needed to import data into Azure ML using the Data Import feature. You can also use the API and not the web interface or Web Studio interface to create connections to Git repositories like those available on GitHub, or to container registries or Python feeds. In this video, you learned about data assets, data stores, dataset monitors, data importing in Azure ML Studio, and data connections in Azure ML Studio. Each solution has unique strengths suited to different types of data, whether structured or unstructured. By selecting the appropriate storage solution, you can ensure better efficiency, scalability, and data management for your machine learning projects. To reinforce what you've learned, take some time to experiment with those Azure storage solutions in your environment. Practical, hands-on experience is crucial for building a deep understanding of how these tools can be used to optimize machine learning workflows.
Have you ever spent hours cleaning data and setting up a training process only to realize your model isn't performing as expected? Data preparation and training can be both overwhelming and time-consuming. But with Microsoft Azure, these processes become streamlined, efficient, and scalable. Today, we're going to show you how to leverage Azure's tools to get your data and models ready for success. By the end of this video, you'll be able to describe the key steps involved in data preparation for machine learning projects. You'll learn best practices for using Azure Machine Learning tools to automate data preparation and model training. You'll also gain insight into why Azure is a powerful platform for scaling machine learning workflows. Data preparation is all about getting your data ready to be used by machine learning algorithms. It involves processes like data cleaning or removing inconsistencies or filling in missing values, data transformation, and feature engineering. Properly preparing your data ensures that your model is learning from the right inputs, which is critical for achieving high performance. To prepare a data ingestion pipeline in Azure, follow these steps. First, define your data source. Identify the different data sources you'll be ingesting data from, which could include databases, file storage, APIs, or external data services. Next, use Azure Data Factory to automate the ingestion process. Azure Data Factory provides a range of connectors that make it easy to pull data from the identified sources. After ingestion, use Azure Data Factory's mapping data flows to transform the raw data into a usable format. This includes operations like filtering, aggregating, and joining data from multiple sources to ensure consistency. Once the data is transformed, store it in an appropriate Azure storage solution, such as Azure Blob Storage or Data Lake Storage, depending on your project's requirements, of course. This helps ensure that data is readily available for future use. Finally, register the ingested data as a data set in Azure Machine Learning. This makes the data easily accessible for model training and experimentation, streamlining the entire machine learning process. By following these steps, you can create a reliable and efficient data ingestion pipeline that feeds high-quality data into your machine learning workflows. Once your data is ready, it's then time to train your model. Azure Machine Learning makes it easy to run experiments at scale. With compute clusters, you can train models faster by distributing workloads across multiple nodes. Azure Machine Learning also allows you to track experiments, compare different models, and choose the best performing one, all from a single interface. To wrap up, you learned why data preparation and model training are vital components of any machine learning project. Using Azure's integrated tools, you can streamline these processes, making it easier to focus on building and improving your models. I encourage you to explore Azure Machine Learning and start working on your data preparation pipelines today. Get started with Azure Machine Learning by setting up your own data preparation pipeline. Experiment with model training because, after all, hands-on practice is essential to mastering these tools and making your models truly effective.
Imagine you're working for a healthcare company that collects patient data from multiple clinics. You need a way to consolidate, clean, and store that data to make it accessible and reliable for analysis. Without a streamlined process, the task could become overwhelming. In this screencast video, we will walk you through the process of creating an ingestion pipeline step by step. This hands-on walkthrough is designed to help you understand the detailed implementation of a pipeline using Microsoft Azure services to extract, transform, and load data efficiently. Follow along with the video to gain practical experience and observe best practices in action. By the end of this video, you will be able to set up a pipeline, implement data extraction, transformation, and loading processes, and understand how to use Azure monitoring tools to ensure data reliability. First, let's go to ml.azure.com and sign in if prompted. Then, we will click on our workspace to enter it. Under Assets, let's go to Pipelines, and then create New Pipeline. Let's start by creating a basic regression pipeline. Click here to create the regression pipeline. Pipelines in Microsoft Azure can be used to transform raw data into trained models and evaluate those models. Here, we see different blocks being chained together and executed in order to proceed from raw automobile price data to an evaluated model. Double-click on any of these blocks to view more details about them. Here, we can see that this block consumes a URI, a data set at Azure-ML/data/automobile price raw/versions/3. We can then see, for example, by double-clicking here, details on the model training. We can see the run settings, which use the default compute target, component information, node information, and other details on how the model will be trained. We can see here that we are using a linear regression model, which is combined in the next step with the training data from the split data set. Later, the testing data is evaluated on by the model and used to evaluate the model. Let's go ahead and run this pipeline so we can see how well this linear regression model is able to predict automobile price data. Let's click Configure and Submit. For experiment name, let's create new and call it car-price-data-pipeline. We'll leave the job display name as so and click Review and Submit. In some cases, you might not be able to click Submit because you're missing another configuration detail. Things can get pretty crowded pretty quickly here in the GUI of the pipelines page, so go ahead and click Collapse Left Panel to see more details. We can see here that there's an error in our runtime settings. Click on Runtime Settings, and we see that our error message is that we have not selected a default compute to run the pipeline. Select Compute Instance, then select a compute instance in your workspace that's already running. Now we can click Review and Submit, and then Submit. We'll get a notification that our pipeline job has been submitted, and then we can click here to see details on the job. Here we can see that our job has completed. If we scroll down to Evaluate Model and double click on it, we can see the evaluation of our model. Click on Output and Logs. You can see the logs that were made when the evaluation step was run. Now click on Metrics. Here in Metrics, we can see the coefficient of determination, the mean absolute error, and the relative absolute error of our trained model. Let's go back to our healthcare company scenario. A pipeline can help centralize the data, transform it for analysis, and load it into a model for training. By doing so, healthcare analysts can access the latest data for decision-making, improving patient outcomes. In this video, you learned how to build a robust data ingestion pipeline using Azure services, perfect for centralizing and preparing data for analysis. Starting with secure data extraction, you connected to various sources, handled sensitive information, and transformed it and used it for training a model. Finally, you evaluated that model. Now you're ready to set up your own data pipeline using Azure tools. Experiment with different data sources and models to make your pipeline as flexible and scalable as possible. This is a crucial skill for managing real-world machine learning projects.
Imagine building a predictive model to understand customer churn, but the data is a mess. Missing values, inconsistent formats, and unexpected outliers. Without proper data pre-processing, your model might learn all the wrong patterns, leading, of course, to unreliable predictions. In this video, we'll walk through the key pre-processing techniques that can turn flawed data into insight-ready information. Data pre-processing is the foundational step that ensures the quality and reliability of the data used in machine learning models. By the end of this video, you'll be able to explain the purpose and importance of data pre-processing in machine learning. You'll be able to identify key pre-processing techniques such as handling missing values and normalizing data. You'll also recognize how data pre-processing impacts model performance and outcomes, describe the role of data pre-processing in addressing data biases, and ensuring model fairness. Data pre-processing involves cleaning, transforming, and organizing raw data to make it suitable for machine learning. Raw data often contains inconsistencies, missing values, and things we call noise, which could negatively impact model performance. Pre-processing steps helps to ensure that data is complete, relevant, and in the correct format. This process also involves understanding the type and distribution of data across resource types and sources, which helps in deciding appropriate preprocessing techniques. The success of any machine learning model depends largely on the quality of the data on which it is trained. Garbage in, garbage out. If the data is not well prepared, the model will not perform optimally. Preprocessing involves a few things. First, data quality. Properly preprocessed data is free from errors, inconsistencies, and irrelevant information. This, of course, results in more accurate predictions. Feature scaling. Techniques like normalization and standardization ensure that all features contribute equally to the model, preventing any one particular feature from dominating. Handling missing data. Filling or removing missing values ensures that models can be trained effectively without being affected by gaps in our data set. There are also 4 key steps involved in data preprocessing. First up, data cleaning. Removing duplicates, handling missing values, and correcting errors. Data cleaning may also involve identifying outliers and deciding whether to remove them or modify them. Next is feature selection. Identifying the most relevant features that have a significant impact on model performance. Feature selection can significantly reduce model complexity and improve training efficiency. Next is normalization. Scaling features to bring them into the same range, which helps models learn more effectively. Normalization helps prevent certain features from disproportionately influencing the model. Then there's data encoding. Converting categorical data into numerical formats so that machine learning algorithms can process them. Techniques like one-hot encoding and label encoding are commonly used. One-hot encoding converts categorical data to a binary representation, and label encoding converts categorical data to a numerical representation. Let's return to our customer churn scenario from earlier. You might implement data preprocessing steps like imputation for missing values, normalization of call duration, and standardize address formats to help improve the overall data quality and model performance. In this video, you learned that data preprocessing is a critical step that can make or break a machine learning project. It ensures that the data is suitable for training, leading to more reliable and ultimately more accurate models. By investing time and resources into preprocessing, you set a strong foundation for successful machine learning outcomes. Remember, preprocessing not only helps improve accuracy, but also ensures the model is both fair and unbiased. Think about a data set you've worked with in the past or one you plan to use. What preprocessing steps would you need to take to ensure that data is ready for analysis? Consider not only handling missing values, of course, and scaling features, but also addressing potential biases in the data. Take time to explore these techniques and consider their impact on the overall quality of your data.
Picture this. You're working with a financial data set to predict loan defaults, but the data is a mess. Missing incomes, outliers in credit histories, and inconsistent job titles all threaten to derail your model before you even start. In this walkthrough, we'll show you the step-by-step preprocessing techniques that will turn this chaotic data into a solid foundation for building a powerful predictive model. By the end of this walkthrough, you will be able to apply data cleaning techniques such as handling missing values and correcting errors, use feature scaling techniques to ensure data consistency, encode categorical variables and perform feature selection, detect and appropriately handle outliers, and transform the data to make it more suitable for modeling. First, let's begin by going to ml.azure.com in our web browser, pressing enter, and signing in as needed. Then, we will enter our workspace and create a new Jupyter notebook. Let's call this one cleaning.ipynb. Then, make sure to collapse the File Explorer to make it easier to view your work. Also, make sure your compute instance is running, and click Start Compute if it isn't. Let's define the dataset we'll use as an example in this video. I will copy and paste this code. It will also be made available to you to copy and paste. I'll paste it here and wait until my compute instance has started to run the code. With my compute instance now started, I'll make sure that I've selected Python 3.8-Azure ML as the correct kernel. Wait for the kernel to launch, and then press Shift and Enter to run the code and proceed to the next cell. What we do here is generate a synthetic dataset for testing. We will create a dataset with columns income, credit score, job title, and target, and define the income, credit score, job title, and target of each row. Then we will introduce some missing values and outliers for testing that we will later try to identify and correct. First, you need to handle missing values using imputation techniques like mean or median replacement, and remove duplicate entries to ensure consistency. I will copy and paste this code, which will also be made available to you to copy and paste. I press Shift-Enter to run the code. What this code does is handle missing values by filling the data with the median, and then it removes any duplicates using pandas. Next, standardized numerical features using scikit-learn's standard scaler to ensure that all features are on the same scale, which helps prevent one feature from dominating the model. I paste this code and press Shift-Enter to run it. From scikit-learn.preprocessing, we import standard scaler, create a new standard scaler object, and then use it to scale our data to fit on the same scale. The next step is to convert categorical features into numerical format using one-hot encoding to make them suitable for machine learning algorithms. I copy and paste this code and press Shift-Enter to run it. After that, detect outliers using z-score analysis and remove them to maintain data integrity and reliability. Here, we use NumPy and SciPy to detect and remove outliers using a z-score. If the value of the data is greater than or less than 3, we drop it. Now, you should apply logarithmic transformation to reduce skewness in skewed features, making the data more suitable for modeling. The on-screen code snippet demonstrates this action. Here, we apply log transformation to our data. We'll ignore this error message for now. We may deal with it later when we troubleshoot dataset cleaning. Finally, let's split the dataset into training and testing sets for model evaluation. I'll copy and paste my code and then press Shift-Enter to run it. Here, from scikit-learn.model-selection, we import train-test-split, then use train-test-split to split the dataset into training and testing sets. Let's go back to our financial dataset example. By following the pre-processing steps shown in this walkthrough, you can fix things like missing incomes, outliers in credit histories, and inconsistent job titles to ensure that the data is ready for effective model training, improving the quality and reliability of predictions. In this video, you learned the essential pre-processing steps to transform messy, real-world data into a reliable foundation for predictive modeling. Starting with missing value imputation and duplicate removal, we walked through standardizing numerical features, encoding categorical variables, and removing outliers. We also covered transformations to address skewed data. And finally, prepared the data for training and testing, setting you up for successful machine learning. Now, take the next step by selecting a dataset and implementing each of the pre-processing techniques demonstrated in this video. Focus on handling missing values and scaling your numerical features to see how well prepared your data becomes for model training. Practicing these steps with your own data will help reinforce these critical pre-processing skills.
What makes a model capable of predicting real-world events with precision? How does it go from raw data to insight? In this video, we'll reveal the essentials of model training, showing you why it's the backbone of any successful machine learning project. Are you ready to see what brings a model to life? By the end of this video, you'll be able to explain the importance of model training in understanding data and minimizing errors. You'll be able to describe key motivations for effective model training, including learning from data and achieving generalization. You'll also be able to discuss practical examples that illustrate the impact of model training on real-world applications. Model training is the process through which a machine learning model learns from the data it has been provided. During training, the model is exposed to a labeled data set, allowing it to adjust its internal parameters to minimize errors and improve predictions. The training process typically involves iterative learning, where the model makes predictions, calculates errors, and refines its understanding by adjusting those internal parameters. Model training is extremely important for several reasons. First, learning from data. The core purpose of model training is to enable a machine learning model to understand underlying data patterns. Without proper training, the model cannot generalize well, resulting in, of course, poor predictive performance. Next, minimizing errors. Model training helps to minimize prediction errors through iterative learning. Each iteration allows the model to refine its internal weights and parameters, making it more accurate over time. Next, generalization. A well-trained model generalizes well to new or unseen data. This process is crucial for applying machine learning solutions in real-world scenarios where data can vary significantly from the established training data set. There are two key phases of model training. First up is training the model, trained by feeding it input data along with the correct output, labeled data. The model uses this information to adjust its internal parameters to reduce prediction errors through the iterative learning process, which we've already discussed. Afterward comes evaluation. After training, the model is evaluated on a separate testing set to determine its performance. Evaluation helps identify if the model is overfitting or underfitting and whether further adjustments are required. Imagine, for example, you're developing a model to predict customer churn for a telecom company. Training involves feeding the model with, for example, historical customer data. It includes information about customer usage patterns, complaints, billing information, and customer support interactions. By learning from this data, the model can predict which customers are likely to leave the service, allowing the company to take proactive steps to retain them. The duration of model training depends on several factors, including the size of the data set, the complexity of the model, and the computational resources available. Simple models trained on small data sets can complete training in minutes, whereas complex models like deep neural networks can take hours, days, or, believe it or not, even entire weeks to train. The training process is often monitored using metrics such as loss or accuracy measured over epochs. Training is considered complete when the model's performance on the validation set stops improving. This point is typically identified by monitoring metrics such as validation loss or accuracy. If these metrics plateau or start to worsen, it may indicate that the model is overfitting and training should be stopped. Techniques like early stopping, a method used to stop training once the model's performance on the validation set stops improving, can be used to halt training once the model reaches optimal performance without reaching that final stage of overfitting. In this video, you learned how model training is a pivotal part of the machine learning workflow, transforming raw data into meaningful predictions through iterative learning. A well-trained model is capable of generalizing to unseen data and making accurate predictions. The quality of training data and the appropriateness of the chosen model are critical factors that determine the success of any machine learning project. Think about a data set or problem that interests you. What kind of model would you train to solve that problem? Consider how the model training process, from iterative adjustments all the way to evaluation, would help you achieve your desired outcome.
Imagine you're tasked with predicting financial fraud, but your local machine just isn't cutting it for the volume of data and complexity of models you need. Now, picture a setup where you can harness the cloud's power to train your model on high-performance virtual machines, manage your data, and track experiments, all in one place. In this video, we'll walk you through exactly how Microsoft Azure Machine Learning can make this scenario your reality. By the end of this video, you'll be able to register datasets within Azure Machine Learning and train a model using the Azure Machine Learning SDK. Before we begin, note that training machine learning models can be computationally intensive, especially for deep learning models or large datasets. The CPU speed and number of cores significantly affect how quickly a model can be trained. When creating a compute target, consider selecting a VM size with appropriate resources for your model's complexity. For small models, standard CPUs may suffice, but for complex models, GPUs or more powerful virtual machines will be necessary to reduce training time. Let's start by going to ml.azure.com and signing in if needed. You'll also need to start by creating a new environment and compute instance. To do this, refer to previous instructions in the course. I'll enter my workspace and scroll down to Manage and then Compute to make sure that my compute instance is running. Then I will go to Authoring, then Notebooks, and then create a new file. I'll then close the File Explorer to give a better view and make sure that Python 3.8 Azure ML is my selected kernel. First, register the dataset to be used for training. This allows you to track, version, and reuse your data within the Azure environment. Registering datasets ensures that you can easily access and share them across experiments and keep track of their versions. I will copy and paste this code into my Jupyter Notebook. It will be made available to you to copy and paste as well. I will then press Shift and Enter to run the code. What this code does is connect to our Azure ML workspace and then creates a data store, connects to the default data store within the workspace. For this demonstration, we'll just create a dummy data set as a placeholder. We'll use pandas and string IO to create this data set with the columns age, income, and target, and then fill each row. Then we will save it to trainingdata.csv, and then register trainingdata.csv as our dataset. And we can see that our dataset was registered successfully. Next, let's make a training script for our job. Expand the File Explorer and create a new file. This will be a Python file, and we will name it train.py. If the name already exists, check the box that says overwrite if already exists, and then click Create. And then collapse the File Explorer to give yourself a better view of the new Python file you've created. I've pasted this code here. It will also be made available to you to copy and paste. This is the code that will run when we submit our job to Azure ML for completion. Azure ML will parse the input arguments, run context, get the dataset by its name, convert it to a data frame, and then confirm that it has been loaded successfully and is ready for further preparation and training. Click the Save icon near the top left. Next, use the Azure Machine Learning SDK to train your model. This example demonstrates how to use a simple scikit-learn model for training. Let's go back to our Jupyter notebook. Here, you will define the script that will be used for training, specify the compute target, and pass any necessary arguments. I will copy and paste this code and run it, so I can explain it to you while it is running. I paste the code, then press Shift-Enter to start running it. Here, we have some imports from the Azure ML SDK. First, we will create a new custom environment with the Conda dependencies scikit-learn, pandas, numpy, and joblib. We will also add any pip packages like the Azure ML SDK if needed. Then we will register the environment within our workspace and define the compute instance. Note here that you will need to replace the compute instance name with the name of your compute instance. Then we will define the training script and configuration. This will specify the directory containing your training script and the compute target where the training will occur. The script run config object is used to encapsulate the training configuration, including any script arguments. We'll also pass the dataset as an argument to the script, and then submit the experiment. Finally, we will wait for the completion of the experiment and show the output of the training job. We can see here a very comprehensive set of logs that have occurred from running this training job. We see that the environment was registered successfully and that we were able to complete the run operations. And here is the execution summary. Let's go back to our example of building a predictive model to identify fraud in financial transactions. Using Azure Machine Learning, you can set up a secure workspace, register your transaction dataset, create powerful cloud compute instances, and train a machine learning model. With Azure's capabilities, you can easily track experiment performance and retrain models based on evolving data, making sure your model remains effective in detecting fraud. In this video, you learned how to register datasets within Azure and train a model using Azure Machine Learning SDK. By leveraging Azure's cloud capabilities, you can ensure reproducibility, track performance, and utilize powerful compute resources without managing the infrastructure manually. Try setting up your own Azure Machine Learning workspace and train a simple model using the steps outlined above. Experiment with different configurations and observe how the cloud-based environment can enhance your machine learning workflows.
Did you know that even a small misstep during training can lead to major issues in your final model's performance? What if you had the insight to detect these issues early and fine-tune as you go? Let's explore how monitoring and logging can give you the control you need to steer your training in the right direction every step of the way. By the end of this video, you'll be able to understand the importance of monitoring and logging during the model training process. You'll be able to identify best practices for effective monitoring and logging. You'll also be able to recognize how monitoring impacts model performance and reliability. Monitoring provides real-time insight into the training process, allowing you to keep track of key metrics such as training loss and accuracy. This helps you understand whether the model is learning effectively and identify potential issues early on in the process. Training machine learning models is a complex process, and errors like overfitting, underfitting, or convergence can occur. By monitoring metrics throughout training, you can detect these issues, amongst others, before they become significant. Logging also plays a vital role in optimization by helping identify parts of the training process that may need adjustments, such as changing hyperparameters, modifying the learning rate, or altering the data set to improve training performance. During model training, it is essential to monitor several key metrics. First, training loss. This measures how well the model is learning during each iteration, and a decreasing loss indicates the model is improving. Next, validation loss. This helps identify overfitting by comparing how well the model performs on unseen data compared to the training set. Next, accuracy. This provides an indication of how well the model is predicting correctly during both training and validation phases. Additionally, monitoring the learning rate is crucial, as an inappropriate learning rate, either too high or too low, can negatively affect model convergence. To effectively monitor and log training processes, it is recommended to use dashboards, such as those provided by platforms like Azure Machine Learning, to visualize these metrics in real time. Dashboards make it easy to track the progress of training runs. Setting up automated alerts can help by notifying you if a key metric, such as training loss for example, exceeds a certain threshold. This enables early intervention and prevents wasted compute resources. Granular logging is also important, or logging as much information as possible, including hyperparameter values, data transformations, and model configuration details, which helps in reproducing results and ultimately debugging issues. Experiment tracking tools, like Azure Machine Learning's experiment tracking feature, allow you to manage multiple training runs, compare different runs, observe trends, and select the best performing model for your use case. Imagine, for example, you're training a deep learning model for image classification. During early epochs, you notice that the validation loss is not decreasing while the training loss is. What does this indicate? Overfitting to the data. Effective monitoring allows you to detect this issue early and take corrective action, such as introducing regularization techniques or modifying the training data, ensuring the model's performance is optimized. In this video, you learned how monitoring and logging during model training are critical for understanding model behavior by detecting issues early and ensuring efficient use of resources. By following best practices such as setting up dashboards, logging key metrics, and automating alerts, you can make the training process more reliable and ultimately more effective. Set up monitoring and logging for your next machine learning project. Experiment with different metrics, try using dashboards, and create alerts to get familiar with the tools available for effective training oversight.
Errors can occur at any stage of a machine learning pipeline, and tracking them down can be like finding a needle in a haystack. Today, we'll tackle that problem by setting up a logging system that catches every key event, so you'll never be left in the dark. By the end of this video, you'll be able to set up Python's logging module, log key events during data preprocessing, model training, and inference, and log and handle errors to create a robust and maintainable system. First, we'll set up our Python environment. I'll begin by creating a new Jupyter notebook. Then, I'll make sure that I have selected the Python 3.8 Azure ML kernel. Setting up Python's logging system to capture important events is a critical part of the machine learning Python pipeline. We'll store logs in a file so that they can be reviewed later for debugging or performance monitoring. I'll copy this code and paste it into my Jupyter notebook. Then I will press Shift-Enter to run the code and proceed to the next cell. This step configures the logging system to store log messages in the ml_pipeline.log file. We start by logging an informational message to confirm that logging is working as expected. Next, we'll log the key steps in data preprocessing. This includes loading the dataset, handling missing values, and transforming the data. Logging these actions ensures that we can trace how the data is being prepared for the model. Again, I copy the code, paste it, and press Shift-Enter to run the code and proceed to the next cell. Here, we log the start and completion of data loading and pre-processing steps. We make a log when we start loading the iris dataset from scikit-learn, and then we make another log when we have finished loading the dataset. Then we make a log when we start pre-processing the dataset, and then we pre-process the dataset by searching for missing values in the dataset and replacing them if true, and then logging when we have finished checking for missing values and thus finished data preprocessing. Logging each step of data preprocessing helps track how the data is transformed before training the model. This makes it easier to diagnose issues that may arise from improperly processed data. We'll now log the model training process, including the start of training and any relevant metrics such as training accuracy. If errors occur during training, they will be captured and logged. Again, I copy the code, paste it into my Jupyter notebook, and press Shift-Enter to run the code. Here, we log the start and end of model training along with key metrics. Here, we split the data into training and testing sets using scikit-learn's train test split tool. Then we make a log to note the start of model training, and then we try to create a decision tree classifier and fit that decision tree classifier model to our training data. If successful, we output to our log file that the model was trained successfully, else we output to our log file that there is an error during model training and print the exception. Then we check the accuracy of the model and log the training accuracy of the model. By logging the start, completion, and key metrics of model training, you can track how well the model is performing. Any errors that occur during training are captured and logged for debugging. Finally, we'll log the process of making predictions with the trained model. We'll capture inputs, outputs, and any errors that occur during inference. Again, I paste the code and press Shift-Enter to run it. Here, we log the start of the prediction process and capture the outputs. We log the start of the model prediction process, and then we try to make predictions using model.predict and our test set. If successful, we log that the predictions were made successfully, and if not, we log that there is an error making predictions and log the exception. Then we log a sample of the predictions that were made, taking the first 5. Logging predictions provides traceability for the model's outputs, helping you understand how the model behaves in production or testing environments. Logging a sample of the predictions is useful for verifying that the model is working as expected. To view the log that we've made during this test, you can open the file that's been created called mlpipeline.log and see the events that have occurred. In this video, you learned how to implement logging in a machine learning pipeline to improve transparency, debugging, and performance monitoring. You set up Python's logging module and logged important steps during data preprocessing, model training, and predictions. By logging these key events and capturing errors, you now have a clearer view of how your model operates and how to troubleshoot potential issues. This technique is essential for maintaining robust, maintainable machine learning systems. Now that you've seen how to implement logging Add it to your own machine learning projects. Track important events, capture errors, and improve the reliability of your systems.
Have you ever wondered how machine learning models make their way from development to actually impacting real-world users? In this video, we'll explore model deployment, which provides a high-level overview of what deployment is, why it's important, and how it's applied in real-world scenarios. By the end of this video, you'll be able to understand the concept of model deployment, recognize the importance of deploying machine learning models effectively, and identify common approaches to model deployment and real-world examples. So what is model deployment? Model deployment is a process of making a trained machine learning model accessible to end users or systems for generating predictions. This involves integrating the model into a production environment where it can receive input data, process it, and ultimately provide output. Deployment can take many different forms, such as deploying the model as a web service, embedding it into an application, or using it for batch predictions. The ultimate goal of deployment is to deliver the model's predictions in a consistent, reliable, and efficient manner that meets ultimate user need. So why is model deployment important? Well, the overall purpose of training a machine learning model is to solve a real-world problem or make a specific process more efficient. Deployment is what bridges the gap between development and that real-world application, allowing stakeholders to benefit from the model's insight and predictive power. Without deployment, the value generated by the model remains only theoretical and cannot provide practical benefit. Effective deployment ensures that predictions are made in a timely manner, that the model is reliable under different conditions, and that the system can scale to meet increasing demand. There are several common approaches to model deployment. First, as a web service. One of the most popular ways to deploy a model is by exposing it as a REST API using platforms like Azure Machine Learning, AWS SageMaker, or Google AI Platform. This allows applications to send data to the model and receive predictions in real time. A good example of this is a chatbot sending queries to a model API for customer support responses. Next is batch processing. For use cases where real-time predictions are not necessary, models can be deployed to process data in batches. This is commonly used for periodic analytics tasks, such as, for example, generating daily sales forecasts. Then there's edge deployment. In scenarios where low latency or high speed is crucial, models may be deployed on edge devices. This means the model runs locally on devices like smartphones, IoT or Internet of Things devices, or embedded systems, minimizing the need for data to be sent to a central server. An example of this includes running a predictive maintenance model on IoT devices in, for example, a manufacturing plant. Consider a retail company that wants to improve customer experience by predicting which products a user is most likely to purchase and offering them. After training a recommendation model, it is deployed as a web service. When a customer interacts with the website, the system sends their browsing and purchasing data to the model via the web service, and the model returns personalized product recommendations. By deploying the model, the company ensures that customers receive relevant suggestions in real time, enhancing their shopping experience and increasing sales. In another example, a healthcare provider may deploy a model on an edge device to monitor patient vitals continuously. In this case, the model is embedded in a wearable device to detect anomalies such as, for example, an irregular heartbeat without relying on constant cloud connectivity. This enables real-time alerts and ensures critical health insights are available to both patients and their practitioners without delay. Model deployment is a critical aspect of the machine learning workflow that turns trained models into valuable assets by making them available for use in real-world scenarios. It bridges the gap between data science and practical application, providing the means for insight to be delivered effectively. Whether through web services, batch processing, or edge deployment, choosing the right deployment strategy is essential for maximizing the impact of machine learning models. Reflect on a project where you've trained a machine learning model. How would you deploy it to provide the most value to its intended users? Consider which deployment approach, web service, batch processing, or edge deployment, would best meet the needs of the problem you're trying to solve.
Imagine you've developed a model capable of making impactful predictions or optimizing critical decisions. However, the true power of your model lies in its deployment, ensuring it's accessible, scalable, and ready to deliver real-time insights. In this walkthrough, we'll guide you through the steps of transforming your trained model into a fully operational service on Azure Machine Learning, so it's ready to provide tangible value to end users and applications. By the end of this video, you will be able to configure and navigate the Azure Machine Learning workspace to manage and deploy machine learning models. Describe the steps to deploy a trained model as a scalable service by creating an inference configuration and selecting appropriate Azure compute resources. And test and validate the deployed model endpoint, ensuring reliable predictions for real-world applications. Let's begin by going to ml.azure.com and entering your workspace. I've already entered my workspace here. Next, we will go to Notebooks under the Authoring section. And usually, we find ourselves on the Files tab of the File Explorer. However, today we will go to the Samples tab of the File Explorer. Under Samples, go to SDK v1, then How to use Azure ML, then Deployment, then Deploy to Cloud. Click on Model Register and Deploy.ipynb to open the Jupyter Notebook. Now, click Clone this file to copy this file and its associated files to your workspace. I'll put it here under the folder Cloned from Samples that I've already created. Then I will click Clone. Here, we can see our Jupyter Notebook, a YAML file, a readme.md file, and a Python file have been cloned to our workspace. Now, I will close the File Explorer to make the Jupyter Notebook easier to view. These sample activities are provided by Microsoft to help people learn how to use Azure Machine Learning Studio. They are a useful learning resource and can be used at any time. Let's run through the prerequisites of this exercise. First, we will run this code cell to import azureml.core and make sure we're using the correct SDK version. Since we cloned this Jupyter Notebook from the SDK v1 library, we have to make sure we are using the Python 3.8 Azure ML kernel. The next step is to initialize our workspace. I'll press Shift-Enter to run this code cell. And here we see we have imported the workspace and created a workspace object from our existing configuration. The next step is to create a trained model. For this, we will use scikit-learn to train a small model on scikit-learn's diabetes dataset. I'll press Shift-Enter to run this code and proceed to the next cell. The next step is to register input and output datasets. I'll press Shift-Enter again to run the code. Here, we save two files, features.csv and labels.csv, and register them in our workspace. The next step is to register the model using the model.register function. In addition, registering the model will store model metadata like description, tags, and framework information. This can be useful later when dealing with many registered models. I'll press Shift-Enter to run this code and proceed to the next cell. Registering a model is also a critical part of deploying it. You must register a model before you can deploy it. Here, we define the workspace associated with the model, its framework, its path, its input dataset and output dataset, and the resource configuration necessary. In this case, we can run the model with only one CPU and half a gigabyte of memory. Here, the model's description lies: ridge regression model to predict diabetes progression. Next, we will deploy the model. We will not use the default environment because Microsoft may change the default environment over time. And in fact, as of time of recording, the default environment no longer works with this model. This model is no longer supported. So instead, we will scroll down and use a custom environment instead. Custom environments provide more secure and more defined ways to run models in production environments. Here, we are using specific versions of pip and loading the packages Azure ML defaults, inferred schema, joblib, and specific versions of dill, numpy, and scikit-learn. Here, I'll click inside the code cell and press Shift-Enter to run it. We will also add Python code for initializing and running our model. Here's an example script. I run this code to print the file score.py. This is the contents of the file score.py. We can see we import joblib, numpy, and os, call the initialization method, specify the model file name, path, and model, and then call run using model.predict on the data that has been passed into the model, and then returning the result in list form. Now, we will deploy our model. Here we will use inference config and model.deploy to deploy our model. I will press Shift-Enter to run the code. This next step may take several minutes. After about 8 minutes, our deployment has successfully completed. We can view the output logs here. If you have any errors with your deployment, you'll see a message here that can give you some troubleshooting help for getting your cluster to work. After your model is deployed, we can test it using input payload and service.run. I'll run this code cell. Remember to first modify the code cell to import JSON and run it again. And now we see, giving this data into our model, the model returns this output data. Now that we've finished testing our service, we can clean up the deployment using service.delete. This will delete the service, causing it to stop running and preventing unnecessary charges being added to your account. Let's apply this to a real-world scenario. Suppose you have built a recommendation model to suggest products to customers in an e-commerce application. Deploying this model as an API allows the website to request product recommendations for each user in real time. This requires the model to be deployed in a scalable environment, such as AKS, to handle high volumes of requests. By setting up monitoring and alerts, you can also ensure the service maintains optimal performance even during peak traffic periods. Deploying a trained model correctly is essential for delivering the value it was designed to provide. By following these steps, setting up a workspace, registering the model, creating an inference configuration, deploying the model, and testing it, you can ensure your deployed service is robust, scalable, and reliable. Remember that proper deployment practices are key to maximizing the utility and performance of your machine learning models. Take what you've learned in this walkthrough and try deploying a different model to Azure. Experiment with deploying to different compute targets, such as Azure Kubernetes Service, to gain experience with managing large-scale model deployments. Are you ready to scale your machine learning models seamlessly? In this screencast, we'll dive into the essentials of deploying models with Azure Kubernetes Service, or AKS. By following best practices, you'll learn the most efficient way to set up, manage, and scale your deployments, ensuring reliability and performance every step of the way. By the end of this video, you'll be able to set up an Azure Machine Learning workspace, deploy models to AKS, and test deployed models. To begin, let's go to ml.azure.com and sign in if prompted. Then, enter your workspace. Click on your workspace, then click on the Notebooks section. In your File Explorer, switch from Files to Samples. Under Samples, let's navigate to SDK v1, How to use Azure ML, Deployment, Production Deploy to AKS, and finally click on Production Deploy to AKS.ipynb. This is a Jupyter Notebook provided by Microsoft to teach you how to deploy a web service to Azure Kubernetes Service or AKS. Let's click Clone this notebook and select a spot in our files where we can clone this notebook and its listed dependencies here. Make sure to clone to a directory that you haven't cloned to before to avoid any dependency issues. Let's clone to the dweaver directory. I'm sure dweaver won't mind that I'm using her directory to clone this notebook. Now the freshly cloned notebook should be available to you here. Let's collapse the File Explorer to make things easier to see. Make sure that your compute instance is attached and running. Start running it if it isn't. And because we cloned from the SDK v1 directory in the samples directory, make sure that Python 3.8-AzureML is the selected kernel. Now let's discuss deploying a web service to Azure Kubernetes Service. This notebook will show the steps for deploying a service, including registering a model, creating an image, provisioning a cluster, and deploying the service to the cluster. We'll then test and delete the service, image, and model. Let's begin by running these imports. I will click the Run Cell button to run the code within one of these code cells. I'll click the same thing here to import the Azure ML SDK and print the Azure ML SDK version in this environment, which here is 1.57.0. Now, let's load the existing workspace from the config file. I'll run the cell and load the workspace from config. Then I will print the workspace name, resource group, location, and subscription ID to make sure everything has loaded properly. The next step is to register an existing trained model that was cloned when we cloned this Jupyter Notebook. I'll run the cell to register a model called sklearn regression model.pkl. This is a ridge regression model to predict diabetes. Next, let's create an environment that the model will be deployed with. On a Kubernetes cluster, we will deploy an environment that will define certain things like conda packages and numpy packages that our model needs to function. For us, those conda packages are numpy, scikit-learn, and scipy, and the pip packages are Azure ML defaults and inference schema. Let's run the cell. We can also consider using a custom Docker image to further specify the environment. Next part is to write the entry script. We will write the script here that will be used to predict on your model. Here, we will write this code here to a file called score.py. We define an initialization function, which gets the sklearn regression model.pkl that we already registered, and then loads it using joblib. Then we define a run function. The run function will load raw data using JSON, and then load it into a numpy array using numpy. Then the result will be made using the model's prediction on the data from numpy, and then we will return the result in list form. We will also catch and handle any exceptions here. The next step is to create the inference config. The inference config will be used when deploying the model. I will click Run Cell to create the inference config. This next step is optional. It's model profiling. Model profiling helps you understand how much CPU and memory the service needs to function. Model profiling will help you understand how much CPU and memory resources to attach to your Kubernetes cluster. This process, though, is very time consuming. It can take up to 25 minutes to model to profile just one model. So we'll skip it here. The next step is to provision the AKS cluster. You'll probably run into an issue here because by default, an AKS cluster, when provisioned, will request 12 virtual CPUs. You are most likely operating in an environment in Azure where you have a quota of 10 virtual CPUs, meaning that the deployment will fail. If you're working in a production environment at an organization that is trying to solve a machine learning problem, you'll be given a larger quota that will allow you to deploy a cluster like this seamlessly. Also, if you upgrade to a pay-as-you-go account within Azure ML and pay for a larger CPU quota, you can run this code and seamlessly provision an AKS cluster. We'll skip it for now. The notebook also shows us optional steps for creating an AKS cluster, like deploying it in a virtual network, or enabling SSL or secure socket layers on it. You know you're connecting to a website over SSL or TLS when you see this lock icon in the URL. Same thing here. Enabling SSL on an AKS cluster means that the data sent and received to the cluster is encrypted so that a third party cannot view it. An optional step is to attach an existing AKS cluster instead of creating a new one as the code earlier defined. Finally, let's deploy our web service to AKS. We will call AKS web service.deploy configuration. Then we will call model.deploy to deploy our model to the cluster. We will wait for deployment to finish and then print the service state of the AKS service. Finally, we'll test our web service using the run method. Here, we import JSON, define a test sample of data to send to the cluster, and then ask the cluster to make a prediction on it and print the prediction. We can also consider testing the web service using a raw HTTP request. Finally, we should clean up by deleting the AKS service and model. Let's go back to a real-world example. Suppose you are developing a model for customer support automation in a large enterprise. To validate your model, you deploy it using ACI or Azure Container Instance, allowing the internal team to test its functionality. Once validated, you deploy it to AKS to handle a large volume of incoming requests, ensuring high availability for customers. This approach lets you leverage ACI for quick testing and AKS for production-level scalability. Deploying models with Azure Kubernetes Service, or AKS, and Azure Container Instances, or ACI, allows you to address different deployment needs effectively. ACI is perfect for lightweight, low-risk deployments, while AKS is ideal for large-scale, production-ready environments. In this video, you learned how to set up an Azure Machine Learning workspace, deploy models to AKS, and test deployed models. Try deploying a model to both ACI and AKS. Practice adjusting the deployment configurations to understand how CPU, memory, and different compute targets impact the performance and scalability of your deployment. Imagine you're working on a sensitive AI/ML project, and you need to access some resources from within a Python script. How does Azure Machine Learning know that it's you trying to access the resources and not an attacker trying to steal your data? In this screencast, we'll discuss Azure Authentication. By the end of this video, you will learn how to authenticate to your Azure ML workspace using Interactive Login Authentication, Azure CLI Authentication, Managed Service Identity or MSI Authentication, Service Principal Authentication, and Token Authentication. Let's begin by going to ml.azure.com and signing in if prompted. From here, open your workspace and click on Notebooks. Usually we go to the Files tab, but today we'll go to Samples. Click on Samples, and then SDK v1, and then How to Use Azure ML, and then Manage Azure ML Service, then Authentication in Azure ML, and finally click on Authentication in Azure ML.ipynb. This is a Jupyter notebook that will teach us how to handle authentication in Azure Machine Learning. Click Clone this notebook, and then click a folder in your workspace where you want to clone this notebook and its dependencies. Azure Machine Learning should automatically open the cloned notebook. Click Collapse File Explorer to give yourself a better view of the notebook. Then, make sure your compute instance is running and click Start Compute if it isn't. In the meantime, let's talk about the different authentication methods in Azure Machine Learning that we'll cover. The first is interactive login authentication, then Azure CLI authentication, then Managed Service Identity or MSI authentication, Service Principal authentication, and finally token authentication. Let's wait for our compute instance to finish loading. Now that our compute instance has started, make sure that Python 3.8-Azure ML is the selected kernel. Now, let's import workspace from azureml.core. Click the Run Cell button, and then let's proceed to interactive authentication. Interactive authentication is the default mode when using Azure ML SDK. If you do workspace.fromconfig equals ws, then you will get an interactive login dialog. Click Run Cell. Our workspace has already been configured, so an interactive dialog does not pop up. If you explicitly specify the subscription ID, resource group, and workspace name, you may get a dialog. You can find the subscription ID, resource group, and workspace name by clicking up here near the top right by Change Workspace. You will see your current subscription, workspace, resource group, subscription ID, and location. Click Cancel to close this box. If you see this message saying all the subscriptions that you have access to, and then an empty array, this means you need to do further authentication with Azure Active Directory, formerly known as Azure Active Directory, currently known as Entra ID. You can configure Entra ID at portal.azure.com. Let's proceed to Azure CLI authentication. If you have installed the Azure CLI package and used AZ login in a terminal to log into your Azure subscription, you can use the Azure CLI authentication class. Let's run this code. Here, we see that we could not retrieve the user token because we have not yet run AZ login. To do this, we can click on the three dots here and click Open Terminal. Now let's try running AZ space login and then press Enter. Now we are prompted to go to this page and enter this code here. I'll paste the code, click Next, click My Account, and yes, I'm trying to sign in with the Azure CLI. I'll click Continue. And now I've signed in with Azure CLI. I can now close this tab. Coming back to our Jupyter Notebook, let's try running the CLI authentication cell again. This time, we see that we are authenticated but get a different error related to permissions. Apparently, we don't have permission to access my subscription ID. This is a configuration issue, but we've successfully authenticated ourselves with Azure using this method. The next method is MSI authentication. Note that this authentication is only supported when using the software development kit from an Azure virtual machine. This code will fail on a local computer. Let's try running it. Again, we get the same error message here, indicating that we have successfully authenticated ourselves, but do not have permission to view this subscription, my subscription ID. This is probably because our subscription ID is different from the one used in the Jupyter Notebook. Next is Service Principal Authentication. Service Principal Authentication can be created by going to the Azure portal, selecting Azure Active Directory or Entra ID, and App Registrations. Then click New Application and give your service principal a name. Then click Register. Here, you will copy the application ID and tenant ID as they will be needed later. Then, select Certificates and Secrets and create a new client secret. Finally, you need to give the service principal permissions to access your workspace using Identity Access Management within Entra ID. Add a role assignment and click Save. Now you're ready for Service Principal Authentication. One issue that you need to be cognizant of is the risk of leaking your password when sharing code with other people. For this reason, it is highly recommended to store your password as an environment variable and read the environment variable with your script. This way, if you share your code with other people, your password will not be shared with them, as it will only be stored as an environment variable on the machine you're running the code on. Finally, token authentication. When token generation and its refresh needs to be outside an AML SDK, we recommend using token authentication. It can be used for getting token for AML or ARM audience, thus giving more granular control over the token generated. Token authentication allows us to authenticate with Azure ML from outside an Azure ML environment. And now, using secrets in remote runs. Sometimes you have to pass a secret to a remote run, for example, a username and password, to authenticate against an external data source. Azure ML SDK enables this case through Key Vault associated with your workspace. On a local computer, you can read in a local secret, for example, from an environment variable or user input. Then you can obtain a reference to the Key Vault and then add the secret name-value pair in the Key Vault. The secret is then available for remote runs as shown further below. And that's that. In this video, you learned about authentication within Azure Machine Learning. Now it's your turn to put this into practice. Make sure that your Azure Machine Learning applications are handling authentication properly, and that your passwords or secret access tokens are not being leaked, and that you have locked down your application to make sure that it cannot be accessed by unauthorized individuals, whether inside or outside of your organization.
Imagine deploying machine learning models faster, with fewer errors, and on a larger scale. This is the power of CI/CD pipelines. Let's dive in and see how CI/CD can transform the way you deploy your models. By the end of this video, you'll be able to understand what CI/CD pipelines are and their role in automating model deployment. You'll recognize the benefits of using CI/CD pipelines in machine learning projects and identify examples of CI/CD pipeline tools and their associated use cases. So what is a CI/CD pipeline? CI/CD stands for continuous integration and continuous deployment. A CI/CD pipeline is an automated set of processes that developers use to build, test, and deploy code more efficiently. In the context of machine learning, CI/CD pipelines help automate model retraining, testing, and deployment, reducing the time and manual effort required to bring new models or updated versions into production. Continuous integration, the CI half, focuses on merging code changes into a shared repository, running automated tests to catch integration issues early. Continuous deployment, the CD half, on the other hand, is about automating the deployment of these changes to production environments once they pass all the associated tests. This allows teams to update models more frequently and confidently, knowing that each update has been rigorously tested. The primary motivation for using CI/CD pipelines is to reduce manual errors, improve productivity, and ensure consistent deployment processes. In machine learning projects, models often require frequent updates due to changes in data or improved techniques. By implementing CI/CD, data scientists and engineers can ensure that models are retrained, validated, and deployed automatically without requiring extensive manual oversight. For example, consider a recommendation model for an e-commerce platform that needs to be updated weekly with new customer data. A CI/CD pipeline allows data scientists to integrate the new data, retrain the model, run tests, and deploy the updated model seamlessly. This automation accelerates the time to market for new models and ensures that users are always served the most up-to-date version. There are a few key components of a CI/CD pipeline. And a typical pipeline for machine learning involves several stages. First, source control. All model scripts, configuration files, and dependencies are stored in a version-controlled repository like GitHub or Azure repos. Next, build. The build stage involves creating the required environment, installing dependencies, and ensuring that all the components are correctly set up. Then comes testing. Automated tests are run to validate the performance of the model, including unit tests for the code and validation tests for model accuracy. Then there's deployment. Once the model passes all tests, it's automatically deployed to the target environment, such as Azure Kubernetes Service, AKS, or Azure Container Instances, ACI. There are some tools commonly used in CI/CD pipelines. Let's explore those now. First up, Azure DevOps. This provides end-to-end capabilities for managing CI/CD pipelines, integrating with Azure Machine Learning for automated model retraining and deployment. GitHub Actions. This tool allows for automating workflows, including CI/CD for machine learning projects, directly from GitHub repositories. Note, by the way, this tool is not covered in this course. We include it here for the sake of thoroughness. Then there's Jenkins. This is an open source automation server that can be used to build and manage CI/CD pipelines for various types of projects, including machine learning. Also note, this tool is not covered in this course. Consider a financial institution using a fraud detection model. As fraud patterns change, the model needs to be updated frequently to ensure accuracy. A CI/CD pipeline is set up to automate that process. New data is added weekly, the model is retrained, and undergoes validation tests. If the updated model meets the required accuracy, it is automatically deployed to production. This not only saves time, but also ensures the model is continuously improving to detect new types of fraud effectively. CI/CD pipelines are crucial for modern machine learning development, providing a reliable and automated way to integrate changes, test models, and ultimately deploy them into production. By reducing manual intervention, CI/CD ensures faster, more consistent, and scalable deployments, making machine learning models more adaptable to changing data and requirements. Reflect on your current model deployment process. Could you benefit from implementing CI/CD pipelines to automate testing and deployment? Start experimenting with tools like Azure DevOps or GitHub Actions and see how they can streamline your workflow. Are you wondering how to keep your machine learning models performing at their best after deployment? In this video, we'll explore best practices for managing and monitoring models post-deployment. By the end of this video, you'll be able to understand the importance of model management after deployment, explain how to implement monitoring techniques to track the health and performance of machine learning models in production, and explain how to apply best practices for updating and maintaining deployed models. Once a model is deployed, managing it effectively is key to ensuring it remains accurate and useful over time. Model management involves tracking the model's versions, maintaining metadata, and scheduling updates. Let's begin with version control. Always version control your models to ensure traceability. Tracking different versions of the model helps understand which version performs best and makes it easier to roll back to a previous version if necessary. Tools like Azure Machine Learning or MLflow can assist in managing model versions. Next, model registry. Use a model registry to store and manage models. A model registry acts as a centralized store where models, metadata, and deployment history can be tracked. This helps streamline the process of deploying and updating models across different environments. Next is automation and scheduling. Automate the retraining and redeployment of models when new data is available. Scheduling model updates can help ensure that your model remains current and continues to perform well when data inevitably changes. There are a number of monitoring techniques as well. These are crucial to identify and resolve issues like model drift, data quality problems, or drops in performance. Let's begin with model drift detection. Model drift occurs when the data used in production no longer matches the data on which the model was trained, leading to a degradation in performance. Use monitoring tools to compare the current data distribution with the training data distribution and trigger alerts if significant deviations are detected. Next is performance metrics tracking. Continuously track key metrics such as accuracy, precision, recall, latency, or error rate to ensure the model is performing as expected. Monitoring these metrics helps in identifying performance degradation early on. Next, logging and alerts. Use logging to track the model's inputs and outputs over time. Implement alerts to notify you if a specific threshold has been breached, such as increased error rates or latency. This allows your team to respond promptly to issues that may arise. Consider, for example, a financial services company using a machine learning model to detect fraudulent transactions. After deployment, it's crucial to monitor the model's accuracy and track any false positive or fake negative rates. If the model starts flagging too many legitimate transactions as fraudulent, this could indicate a need for retraining with more recent data. Automated drift detection tools can trigger retraining when significant changes in transaction patterns are detected, ensuring the model remains effective. Let's talk about best practices for model management and monitoring. First up, the automation of retraining. This ensures the model stays up to date without requiring any manual intervention. Next up, a centralized monitoring dashboard. Use a centralized dashboard to monitor multiple deployed models. Tools like Azure Monitor or Grafana can help visualize metrics, making it easier to identify issues. Failover mechanisms. Implement failover mechanisms in case a model deployment fails or shows degraded performance. Having a backup model or fallback system ensures continuity of service and minimizes the impact on users. In summary, you've learned why model management and monitoring are essential aspects of the machine learning lifecycle that ensure deployed models continue to provide value. By following these best practices, you can maintain model accuracy, detect performance issues early, and ensure a seamless experience for your end users. Take the time to implement monitoring tools for your deployed models. Experiment with different metrics and dashboards to find the most effective setup for keeping track of your model's health and your model's performance.
Want to keep your machine learning models performing at their best even after deployment? In this screencast, we'll walk through the correct and effective approach to monitoring deployed models. Proper monitoring ensures that models remain accurate, reliable, and adaptable to changes in the production environment. This session will cover essential steps, best practices, and tools to help you establish robust monitoring for long-term model success. By the end of this walkthrough, you will be able to understand the critical components of monitoring deployed models, set up comprehensive monitoring using industry-standard tools, and identify common pitfalls and how to avoid them when monitoring models in production. Let's begin by going to ml.azure.com, signing in if prompted, and entering our workspace. Then let's go to Notebooks, Add Files, Create New File, leave the default settings to create a new Jupyter Notebook. Then collapse the File Explorer to give yourself a better view of your Jupyter Notebook. Attach a running compute instance, and make sure you've selected the Python 3.8 Azure ML kernel. The first step in setting up monitoring is choosing the right tools that suit your use case and production environment. Azure Monitor, Grafana, and Prometheus are popular options for monitoring machine learning models deployed on Azure or Kubernetes. Azure Monitor provides comprehensive monitoring for models deployed in Azure environments, enabling easy integration and visualization. Grafana is an open source tool used for creating real-time monitoring dashboards to visualize key metrics. Prometheus is used to collect and store metrics, making it suitable for both model performance, monitoring both model performance, and system-level metrics. The next step is implementing data quality checks. Monitoring data quality is a key aspect of maintaining model reliability. Data quality monitoring ensures that the incoming data is consistent with the data used during model training. Here, we will set up a script to calculate the mean, standard deviation, and range of incoming data features and compare them to training data metrics. I will copy this code and paste it in my Jupyter Notebook. It will be made available to you to copy and paste. Then I will press Shift and Enter to run the code and proceed to the next cell. Here, we manually define a training mean and training standard deviation, and then define some sample incoming data. We calculate the mean of the incoming data and compare it to our training data to check for drift. If drift is detected, we print an alert and take steps to resolve it. The next step is setting up performance metrics monitoring. Tracking model performance metrics is crucial to ensure your model is still performing as intended. Metrics such as accuracy, precision, recall, and F1 score need to be monitored continuously. You can use tools like Prometheus to monitor performance. Here is an example of a Prometheus configuration file. Here, we define a job name, model metrics, and define some static configuration options. The target is hosted on the same computer at port 9090. We won't be covering Prometheus in its entirety today, and this is not valid Python code, so we will create a new code cell and proceed to the next step. The next step is configuring alerts for critical thresholds. To proactively manage issues, set up alerts for key metrics such as accuracy or response time. In Azure Monitor, we can set alerts by setting thresholds for key metrics. For example, we can trigger an email alert if the model accuracy drops below 85% or the response time exceeds a defined limit. I will copy this code and paste it into my Jupyter notebook, and then press Shift and Enter to run it. Here, we can see that we've set an alert condition for an accuracy below 85%. The next step is detecting model drift. Model drift occurs when the underlying data distribution changes, causing the model to perform poorly. Regularly monitor incoming data distributions to detect drift and take necessary actions. You can use statistical tests like the Kolmogorov-Smirnov or KS test to identify significant deviations in data distributions. I will copy this code and paste it into my Jupyter notebook. Then I will press Shift and Enter to run the code. Here, we define an incoming trading data sample and an incoming data sample. Then we perform a KS test to compare the two and see if the two have drifted apart from each other. Step 6 is logging and troubleshooting. Logging model inputs, outputs, and errors is essential for diagnosing issues in production. Effective logging helps to identify problems quickly and take corrective actions. Using logging tools like Azure Log Analytics allows us to store records of prediction requests, errors, and model responses. I will copy this code and paste it here. In this example, we import the logging library. Then we configure our logging settings by specifying a log file and a logging level. Then we log the prediction request and response using logging.info. Let's examine best practices for monitoring deployed models. First is automation. Automate monitoring and alerting to minimize manual intervention. Next is regular updates. Continuously update monitoring scripts to accommodate changes in model and data. Next is scalable infrastructure. Use tools that are scalable and can handle increased data flow as the application grows. Log files can get very big when deploying at scale. Make sure to account for this. Effective monitoring of deployed machine learning models ensures that they continue to perform well in dynamic environments. By choosing the right tools, implementing robust monitoring techniques, and setting up alerts, you can ensure that your models deliver accurate and reliable results. Set up a monitoring of one of your deployed models today. Use tools like Azure Monitor, Grafana, or Prometheus to ensure that you can keep track of key metrics and take prompt action when needed.
Have you ever deployed a machine learning model only to encounter mysterious performance issues or integration headaches that leave you scrambling for answers? By the end of this video, you'll be able to identify common issues that occurred during deployment and operation of machine learning models. You'll also understand the motivation behind effective troubleshooting and the importance of maintaining model reliability, and discuss practical troubleshooting techniques to resolve common deployment problems. When deploying machine learning models, you may face several challenges that can impact the reliability and performance of your model in production. Some of these common issues include model drift, latency issues, data quality concerns, scaling challenges, or integration errors. Here's a brief definition of each and best practices for resolving them. Let's begin with model drift. Over time, the data used for predictions may change significantly from the training data, causing the model's performance to degrade. This is known as model drift and can lead to inaccurate predictions if not properly managed. Next, latency problems. High latency can occur when the model takes too long to respond, affecting the user experience. This issue is often related to insufficient compute resources or inefficient model architecture. Next, Data quality issues. The quality of incoming data can greatly impact model performance. Missing values, outliers, or changes in the distribution of data can cause issues that reduce the accuracy of your model. Then there's scaling challenges. Scaling a model to handle more requests can present difficulties if the infrastructure is not properly optimized. Insufficient scaling can result in high failure rates or increased latency. Then there are integration errors. Integration errors may occur when deploying a model within a larger system, such as an incorrect API call, a version mismatch, or a compatibility issue with other components. Now that we've defined these common errors, let's turn to how to fix them. Follow the best practices below to ensure user satisfaction and minimal downtime. Let's begin by addressing model drift. The solution here is to implement monitoring tools to detect changes in incoming data distributions. Retrain the model regularly or implement a retraining schedule to adapt to these new incoming data patterns. For example, if you observe a drop in model accuracy over time, check if the characteristics of the incoming data have changed. Set up alerts using tools like Azure Monitor to notify you of significant changes in data distribution. Next, let's address reducing latency. The solution here is to optimize the model for inference by reducing its size, using quantization, or deploying the model on hardware with better compute power. For example, using ONNX or Open Neural Network Exchange to optimize your model for faster inference reduces latency and improves response times for the end user. Next, improving data quality. What's the solution here? Set up a data validation pipeline to ensure that incoming data is consistent, complete, and within expected ranges. Data preprocessing steps should be applied here to handle missing values or outliers. For example, you can use Azure Data Factory or similar ETL tools to preprocess incoming data and remove missing values or outliers before feeding it to the model. Next, let's talk about scaling the model. The solution here is to use container orchestration tools like Kubernetes to scale the model automatically based on demand. Ensure the infrastructure has sufficient resources to handle these peak loads. For example, you can deploy the model on Azure Kubernetes Service, or AKS, and configure auto-scaling policies to handle increased traffic during those peak hours. Finally, let's talk fixing integration errors. The solution here is to ensure that all components of the deployment pipeline are compatible, including API versions and their associated dependencies. Regularly test integration points and update them as needed. For example, if your model fails to communicate with a front-end application, check the API documentation for version compatibility and run end-to-end tests to ensure smooth integration. Consider an online financial service using a machine learning model to predict credit risk. If the model starts to exhibit increased latency, users may experience delays in receiving credit approvals, leading, of course, to frustration. By using Azure Monitor to identify high latency, the engineering team can pinpoint the issue, in this case, insufficient compute resources. They can then resolve it by deploying the model on a more powerful virtual machine or optimizing the model's architecture for inference. In this video, you've learned that troubleshooting is an integral part of managing deployed machine learning models. By identifying and resolving common issues such as model drift, latency problems, data quality challenges, scaling issues, and integration errors, you can ensure your model remains reliable and delivers value over time. Reflect on the troubleshooting techniques discussed in this video and consider how you could apply them to your deployed models. What proactive measures can you take to avoid these common issues and maintain high-quality model performance?
Ever get stuck troubleshooting tech problems for hours, only to end up doing an internet search for solutions? What if you had an AI-powered agent to handle those issues for you? In this video, we'll build a smart troubleshooting agent that can diagnose and solve common problems automatically. By the end of this video, you will be able to explain the core components of an intelligent troubleshooting agent, describe how to create a basic knowledge base and implement basic diagnostic logic, and describe how user interaction features are built and automate common fixes. We'll begin by setting up our programming environment. For this project, we are using Python along with libraries like NLTK or Spacey for natural language processing and a simple knowledge base to store our troubleshooting data. I'll begin by creating a new Jupyter notebook. I'll call it Troubleshooting Agent. And we will also create a file for our knowledge base. I will call it Troubleshooting Knowledge Base. .json.json. This setup provides us with the tools to process user input and interaction with the troubleshooting agent. Once we have our environment ready, we can begin building the agent's core functions. The first step in creating an intelligent troubleshooting agent is to build its knowledge base. This is where the agent will store known problems and their corresponding solutions. I've created an example knowledge base, which I will paste here. Here we create a simple JSON file that stores common issues and their solutions. It ensures that the knowledge base is structured in a way that allows easy retrieval of data. The code here shows a sample JSON which includes common issues such as slow internet or a device not charging. The knowledge base is a simple database that the agent will query when diagnosing user-reported problems. The more comprehensive the knowledge base, the more helpful the agent will be in troubleshooting. Next, we'll implement the part of the agent that interacts with the user. Using natural language processing, or NLP, we can make the agent understand user queries and match them to problems in the knowledge base. Let's go back to our troubleshooting agent Jupyter notebook. Let's make sure that Python 3.8 Azure ML is selected. I paste the code. The code will be available for you to copy and paste, and press Shift-Enter to run the code and proceed to the next cell. What this code does is import JSON, pipeline, and Spacey. It will load a pre-trained Spacey model for general natural language processing tasks, and it will initialize a question-answer NLP pipeline. Here, we load the troubleshooting knowledge base, and then we define a function to match user input to the most relevant knowledge base entry. For this, we gather the user input and change it to lowercase. And then, for each issue and details in our knowledge base, we also convert them to lower input and use a natural language processing model to calculate the similarity between user input and symptom text. Here, the similarity is calculated by comparing the natural language processing result of the user input and the natural language processing result of the symptom text. If the similarity is greater than 0.75, 0.75 is just a placeholder here, we return the solution. Else, we say that no matching issue is found in the knowledge base. Then we gather user input, call the function to find the best match, and print out the solution. This code snippet allows the agent to understand natural language input from the user, search for relevant issues in the knowledge base, and provide a solution. It's a simple yet powerful way to make the agent more user-friendly. Let's test it by entering a query. Let's say that the printer is not working, and we are given a solution. Ensure that the printer is connected and check for paper jams. Troubleshooting agents often need to perform diagnostics. We can add a decision-making process that helps the agent ask follow-up questions and perform specific checks before offering a solution. Here we will implement a decision tree or rule-based system to guide the agent through a series of steps for problem diagnosis. We will create conditional logic for common problems like network issues or software errors. I'll add this code to our existing cell. Here, we define a function to troubleshoot internet-related issues with follow-up questions. Here, if the diagnose internet issue function is called, we print, "Have you tried restarting your router?" And then we ask for a response from the user. If the user hasn't restarted their router, we prompt the user to restart their router and check back if the issue persists. If the user already tried restarting, we suggest advanced troubleshooting. Try resetting your network settings or contacting your provider. Let's restart the kernel and run all cells to run the troubleshooting agent with this new logic. I'll give an example query. I'll say that my internet is slow. And then I'm prompted to say, "Have you tried restarting your router?" I will say, "No." And then I am told to restart your router and check if the issue persists. By adding follow-up questions and diagnostic logic, we make the agent more interactive and capable of drilling down into specific issues. This makes troubleshooting more accurate. To speed up the troubleshooting process, we'll add automation for common fixes. This allows the agent to perform simple tasks, like resetting settings, without needing the user to do it manually. Here, we will implement functions that allow the agent to perform simple automated fixes, and we will set up simulated actions like restarting services so that the agent can perform them based on the diagnostic issue. Let's add this code to the decision tree. This code will run when the user says they have an internet connectivity problem, but have not already restarted their router. Automation of common fixes can make the troubleshooting agent more efficient, especially for frequently encountered issues like network problems or system restarts. Let's test this by restarting the kernel and saying that we have an internet problem, that our internet is slow. I will say that I have slow internet, but that I have tried restarting my router. And then the agent will automatically reset some basic network settings by running sudo systemctl restart systemd-networkd.service on my Azure Machine Learning compute instance. This will reset the network adapter on my compute instance and may resolve some common network connectivity problems. In this video, you walked through the process of designing an intelligent troubleshooting agent. You learned how to set up a Python environment, build a knowledge base, implement natural language processing for user interaction, add diagnostic logic, and even automate common fixes for issues like network problems. This step-by-step guide provided the tools and methods needed to create a troubleshooting agent capable of diagnosing and resolving common technical issues efficiently. Now that you've learned how to design a troubleshooting agent, start building one for a specific system or service you use. Customize the knowledge base, enhance the diagnostic logic, and automate fixes to create an efficient, user-friendly troubleshooting experience. Imagine running a machine learning pipeline only to see it fail halfway through due to an unknown error. Logs are piling up, deadlines are looming, and you're not sure where to start. In this walkthrough, we'll guide you step by step through troubleshooting an example pipeline to keep your project on track. By the end of this walkthrough, you will be able to identify and diagnose pipeline issues, apply fixes to common pipeline problems, and implement best practices for monitoring and documentation. First, let's begin by going to ml.azure.com in a web browser and pressing enter. Sign in if needed. Now, let's enter our workspace and then click on Authoring, Notebooks, and then click Add Files, Create New File, and create a new Jupyter Notebook. We'll also close the File Explorer to give ourselves a better view. Make sure your compute instance is running and that you've selected Python 3.8 Azure ML as your Jupyter Notebook's kernel. When troubleshooting pipelines, first identify the problem area. Start by examining the logs generated during the pipeline execution. Logs are invaluable for determining what went wrong and where. Look for specific error messages or warnings that can give clues about the issue. Azure Machine Learning Studio provides detailed logging that can help pinpoint the exact step in the pipeline where the failure occurred. Check the logs for each component, including data ingestion, preprocessing, model training, and deployment. I will copy and paste this code here. This is example code that shows how to access logs from a machine learning pipeline. First, you will import workspace and experiment from azureml.core. Then you will connect to your workspace and create a sample experiment. Once the experiment has been created, you can access the run details by calling experiment.getRuns, and for each experiment.getRuns, print the run ID and the status, and run.getDetails. I can press Shift-Enter to run the code, but nothing will show since we have just created a sample experiment. Try this with an experiment you created by yourself or an example you created earlier in this course to see run IDs and details. Next, check the data integrity. Many issues in a pipeline can be traced back to problems with the data. Validate that the data used in each stage is in the expected format and contains the correct values. If you discover missing or corrupted data, use a data validation script to address these issues before retrying the pipeline. I will copy and paste this example data validation script here and press Shift-Enter to run it. What the script does is create and save a sample data set with a customer ID and membership columns. Customer IDs are numbers and membership levels are either bronze, silver, or gold. We save the dataset to customerdata.csv and then load it back into our file. We validate the data using Pandas data frame tool to make sure that there are no null values in the customer ID column, and that in the membership level column, the only values are bronze, silver, or gold. If there is an error in either case, we print out that message, but since there are no errors, we get the message no null values in column customer ID, and all values in membership level are valid. Next, debug your code in model training. If the problem is in the model training step, isolate the issue by running the training code in a Jupyter Notebook within Azure ML Studio. Running the code step by step will help identify whether there are problems with the hyperparameters, data inputs, or the training algorithm itself. Common issues may include typographical errors, type confusion, or confusing the training and test sets. I will copy and paste this code. It will be made available to you to copy and paste as well. I press Shift-Enter to run the code. What we do here is load the diabetes dataset from scikit-learn. Then we split the data into training and testing sets using scikit-learn's train test split. Then we will create a linear regression model, train the model, and make predictions on the test set. Then we will evaluate the model and output the results. The results are a mean squared error of 2900 and an R2 score of 0.45. The next step is to uncover resource allocation issues. To do this, you can rerun the training code in a Jupyter notebook, taking care to note the memory and CPU usage displayed. I'll press Shift-Enter to run this code again. You may need to restart and run all cells to get a more accurate reading, but note the CPU usage and RAM usage when doing so. Make sure that you're using, again, the same compute instance you're using in your pipeline in your Jupyter notebook to get accurate results. If you see resource exhaustion, consider upgrading your compute instance to a larger one, or expanding the size of your compute cluster. Now, review the deployment settings. If the issue lies in the deployment phase, review the deployment configuration. Ensure that the model has been containerized correctly and that all necessary dependencies are included in the environment. Azure Kubernetes Service or Azure App Services can be used to deploy models, and it's important to verify that the container image is accessible and that network configurations allow communication with other components. I will copy and paste this code. It will be made available to you to copy and paste, but this is just example code. In this example, we connect to our workspace and then load our model. We define the inference configuration and then define the deployment configuration and finally deploy the model using Azure Kubernetes Service. If you run into any issues during this deployment process, you can use print or any other debugging tool to get more details on what is going wrong and where. There are a few more steps to take that I'll cover just briefly, as each of them could be a video of their own. Your next step is to test in a staging environment. Always test changes in a staging environment before applying them to production. Azure ML Studio allows you to create a staging endpoint to validate the changes without impacting the live environment. This can help catch issues that might arise from the updated configuration or code. After that, implement any fixes needed. Once the root cause has been identified, implement the necessary fixes. Update the pipeline configuration, modify code, or adjust data pre-processing steps and processing steps as needed. After making the fixes, rerun the pipeline and observe the results. Make sure to document the changes made so that you can track what modifications resolved the issue. Finally, implement logging and monitoring. Implementing additional logging at each step in the pipeline can provide more detailed information in case issues arise in the future. Tools like Azure Application Insights can be integrated to monitor the performance and identify potential issues early. You can also use alerts to notify you when the pipeline experiences errors or performance degradation. Setting up proactive monitoring helps minimize downtime and ensures quick remediation. In this video, you were introduced to the step-by-step process of identifying and diagnosing pipeline issues by leveraging Microsoft Azure's detailed logging capabilities and validating data integrity. We also demonstrated practical debugging techniques for model training, resource optimization strategies, and best practices for ensuring smooth deployment configurations. Additionally, we discussed the importance of testing changes in the staging environment and implementing robust logging and monitoring systems, such as Azure Application Insights, to proactively detect and address potential pipeline issues. Now that you've learned how to troubleshoot and optimize your pipelines, think about how these strategies can improve the reliability and efficiency of your future projects. As we move forward, you'll gain more hands-on experience to solidify these skills and apply them to real-world scenarios. Get ready to elevate your AI/ML capabilities with Microsoft Azure. Have you ever struggled to identify the root cause of an issue in your machine learning pipeline, only to end up with more questions than answers? In this video, you'll see the proper solution for using diagnostic and monitoring tools in the machine learning pipeline. The goal of this video is to demonstrate the most effective way to implement these tools to identify, troubleshoot, and resolve issues that can impact model performance and reliability. By the end of this walkthrough, you'll be able to Understand how to set up diagnostic and monitoring tools to manage a machine learning pipeline effectively. Learn best practices for identifying and resolving common issues such as data quality and integration errors, and gain insights into how proactive monitoring can improve the model performance and reliability of machine learning models in production environments. First, let's begin by going to ml.azure.com in a web browser, signing in if prompted, entering our workspace, and creating a new Jupyter notebook by going to Notebooks, then Add Files, then Create New File, and then Create. Also, collapse the File Explorer to make your notebook easier to view. Make sure that your compute instance is running, and make sure that you've selected the Python 3.8 kernel. Next, let's choose an appropriate tool for our pipeline. In this example, we will use Pandas for data validation. I will copy and paste this code. It will be made available to you to also copy and paste. I will press Shift-Enter to run it and proceed to the next cell. What this code does is creates a sample dataset with the columns customer ID and membership level. Customer ID is a number and membership level is either bronze, silver, or gold. It creates a data frame using Pandas and saves the data frame to a CSV file named customerdata.csv. Now, to simulate a production environment, we will read the CSV back in and validate the data. We will check that no values in the customer ID column are null, and we will check that in the membership level column, the values are either bronze, silver, or gold, and we will print the results. We see here that there are no null values in the customer ID column and that all values in the membership level are valid. Next, use Azure Application Insights for monitoring to set up metrics collection for the deployed machine learning model. This helps track model performance in real time using latency, throughput, and resource utilization. Set up alerts to notify the team if certain metrics fall below or exceed acceptable thresholds, allowing for immediate action. I'll copy and paste this code. This is just example code that shows how to use Azure Application Insights for monitoring. This code won't run on its own. You'll need to replace my model service with the name of a deployed service in your workspace, and then try running the code. Let's create a new code cell and proceed to the next step. Using Azure Application Insights for monitoring, you can document any issues identified by the tool, such as missing values, high latency, API integration problems. You can also maintain logs of the issues identified, the steps taken to address them, and the results of those steps. This helps build a reference for troubleshooting future efforts. Next, based on the findings, apply appropriate fixes. For example, if data quality issues are found, you can update the data preprocessing steps. Validate that all fixes have been implemented successfully by rerunning the diagnostics and confirming that no new issues arise. Finally, use incremental deployment strategies such as canary deployment to deploy changes with minimal risk. Start by releasing changes to a small subset of users and monitoring their impact. If successful, proceed to a full-scale deployment. I'll copy this code and paste it here to make it available for viewing. Keep in mind, though, that this is just pseudocode and won't run on its own. In canary deployment, you will check to see if your service successfully deployed, if the canary deployment had any issues. If it was successful, then note that the canary deployment was successful and you should proceed to full deployment, making the canary deployment your main deployment. If not, note that the canary deployment failed and that issues need to be investigated before a full deployment of the new version is made. Here you will use monitoring to determine if there are any issues with your new deployment. If there are no issues, you deploy the code to all customers. Imagine you are working with a customer segmentation model used for personalized marketing campaigns. During the diagnostics phase, you use pandas to validate the incoming data and find that many customer records are missing critical fields like customer ID. By addressing these issues upfront, you ensure that the model delivers accurate predictions, leading to more effective marketing efforts. In this video, you've learned how effective use of diagnostic and monitoring tools is key to maintaining the reliability of machine learning models in production environments. By systematically applying these tools, documenting findings, and implementing fixes, you can proactively manage potential issues and ensure your models are performing at their best. Apply these diagnostic and monitoring techniques in your own pipeline by selecting an appropriate tool, validating data, and setting up performance metrics. Start by identifying one aspect of your model's lifecycle to monitor, and see how these strategies improve its reliability and efficiency in production.
Have you ever experienced unexpected drops in model performance only to realize the issue was discovered too late to prevent major impacts? By the end of this video, you'll be able to explain the role of automated alerts and remediation in managing machine learning models in production. You'll be able to describe how automated alerts can help detect potential issues early and trigger appropriate remediation actions. And you'll also be able to discuss examples of effective implementation of monitoring and remediation strategies for machine learning models. Automated alerts and remediation are crucial for managing machine learning models deployed in production. These models often face challenges such as changing data distributions, integration issues, and performance degradation. Without proactive monitoring, it is difficult to identify these problems in a timely manner, which can lead to decreased model accuracy, increased latency, or even outright system failure. Automated alerts notify the operations team when metrics fall outside acceptable thresholds, ensuring timely issue detection. For instance, if latency increases, an alert can trigger immediate intervention. Remediation tools can also take corrective actions automatically, such as retraining a model if drift is detected, reducing the need for manual intervention, and saving time and resources. One example of monitoring and alerting is using Azure Monitor to track model performance in real time. Alerts can be set up for metrics like response time, throughput, or error rate. For instance, a fraud detection model may use a 200 millisecond latency threshold due to its real-time requirements, while a less time-sensitive task might use 500 milliseconds. Azure Monitor can alert the operations team to take action before user experience is impacted. Generally, a developer should configure alerts with thresholds that balance early detection of anomalies and minimizing false alarms. These thresholds should be data-driven, derived from historical performance, and aligned with business impact tolerances to flag critical deviations in key metrics like model accuracy or latency. Another example is automated retraining using Azure Machine Learning. If model drift is detected, a retraining job can be automatically triggered to adapt the model to new data, keeping it relevant, keeping it accurate. Tools like PagerDuty can also be integrated to manage alert response workflows, ensuring that the right team members are notified and can act quickly to resolve these issues. Consider a customer churn prediction model, where performance begins to degrade due to changes in customer behavior. Without automated alerts, these changes might go unnoticed until significant churn has already occurred. By implementing automated alerts and remediation, early signs of model drift are detected. This triggers a retraining job, which then updates the model before customer retention is heavily impacted. Automated alerts and remediation are essential for maintaining reliable machine learning models in production. Implementing proactive monitoring and automated fixes helps ensure that models adapt to changing conditions to minimize downtime. In this video, you learned how automated alerts and remediation are powerful tools for maintaining reliable machine learning models in production. By proactively detecting and fixing issues, these strategies help ensure that models adapt effectively to changing conditions to minimize system downtime. Effective monitoring allows teams to address performance degradation before it causes those significant negative impacts, while automated remediation reduces the need for manual intervention. Think about how these strategies could be applied to your machine learning projects. Start by setting up alerts for key metrics to detect potential issues early, and consider adding automated remediation steps as your model's complexity and deployment needs ultimately grow.
Keeping machine learning models performing well in production isn't easy. From data drift to fluctuating response times, new challenges can emerge at any time. Are you ready to tackle these challenges head-on with automated alerts and proactive solutions? Today, you'll walk through the steps for implementing automated alerts and remediation for a machine learning model in a production environment. This walkthrough aims to demonstrate the best practices for configuring alerts to detect performance issues and setting up automated remediation actions to ensure the model continues to perform optimally. By the end of this walkthrough, you will be able to set up automated alerts for key metrics like response time, accuracy, and throughput. Configure automated remediation actions to address issues such as model drift or decreased accuracy. And describe practical insights into best practices for maintaining the reliability of production-level machine learning models. Let's start by going to ml.azure.com and signing in if prompted. Then we will enter our workspace and click on the Notebooks section and then create a new notebook. Make sure your compute instance is running. Collapse the File Explorer to give yourself a better view. And make sure you've selected Python 3.8 Azure ML as your Jupyter Notebooks kernel. The first step is to set up automated alerts to monitor key performance metrics for your deployed model. For this demonstration, we will use Azure Monitor to track key metrics such as response time and accuracy. You can configure alerts that will notify you if the response time exceeds a certain threshold or if model accuracy falls below a specified level. We will configure an alert that is triggered if the model's response time exceeds 200 milliseconds or if accuracy drops below 85%. Alerts will be sent via email to notify the relevant team members. I will copy and paste this code. It will be made available to you to copy and paste as well. Here, I will press Shift-Enter to run the code and proceed to the next cell. Here, we've used Azure's Identity and Monitor libraries to set up an alert that will take place if the response time is greater than 200 milliseconds. To ensure everything is working as expected, your next step is to test the alerts in remediation setup. In this step, we will manually trigger an alert to verify that both the alert configuration and the automated remediation actions function correctly. I will copy and paste this code. It will be made available to you to copy and paste as well. Then I will press Shift-Enter to run the code. Here, we define a response time and the threshold, 300 milliseconds. Then we simulate an increase in the response time by adding a random number between 100 and 200 to the response time. The response time should now be between the values of 300 and 400. We will check to see if the response time is greater than the threshold, and it is. And then we will print a statement saying that the response time was exceeded. And then we will trigger a notification here. And here is a placeholder for initiating remediation, such as scaling up resources. Manually simulating an increase in response time or reducing the model's accuracy triggers an alert. Verify that the notification is received and that the remediation process, such as retraining, is initiated successfully. I will copy and paste this code. It will be made available to you to copy and paste. In a similar vein, we will also check that the model accuracy alert is working correctly by simulating a drop in model accuracy and running print statements to show that this condition has been satisfied. In a production environment, you would replace this placeholder with an automated retraining of the model or some other automated redeployment action, and also with proper notification. Here are the best practices you should follow for implementing automated alerts and remediation. You should monitor key metrics. Always monitor the most important metrics that directly impact the user experience, such as response time, accuracy, and throughput. Avoid overwhelming the system with too many alerts. Focus on what matters most. Then, you should set appropriate thresholds. Carefully set thresholds for alerts to reduce false positives. These thresholds should be based on historical data and the expected performance of the model. Finally, automate remediation where possible. Automate as many remediation actions as possible to ensure prompt response to issues, minimizing the need for manual intervention. Imagine a healthcare application that uses a machine learning model to predict patient outcomes. By setting up automated alerts and remediation, the healthcare provider can detect early signs of decreased model accuracy due to changing patient data. An alert triggers an automated retraining to update the model with the latest patient data, ensuring that the model's predictions remain reliable and accurate. This proactive approach is critical in high-stakes environments where the accuracy of predictions can have serious implications. In this video, you learned how implementing automated alerts and remediation strategies is crucial for maintaining reliable machine learning models in production. By configuring alerts to monitor key metrics and setting up automated remediation actions, you can proactively address performance issues and minimize model downtime. This walkthrough has provided you with a practical approach to ensuring your model remains effective in a production environment. After watching this walkthrough, try setting up automated alerts and remediation actions for your own machine learning model. Reflect on the metrics that are the most critical to monitor and consider how automated remediation can help you maintain a reliable and high-performing model. Share your experiences and learnings with your peers to discuss best practices for maintaining production-level models. Imagine you need to train a machine learning model, but you don't know how to code and don't have time to learn. How can you make practical use of custom machine learning models without knowing how to code? In this activity, we'll introduce you to automated ML in Microsoft Azure Machine Learning Studio and use it to train a model. By the end of this video, you'll be able to create a dataset in Azure ML Studio and create an automated ML task in Azure ML Studio. In the next video, we'll show you how to navigate model comparisons, generate detailed explanations, and uncover the insights that drive your model's predictions. The first step is to open Azure ML Studio. Go to ml.azure.com in a web browser and press Enter. Sign in if prompted, then click on your workspace to enter it. Next, scroll down in the left section, go to Manage, and then Compute, and make sure that your compute instance is running. If not, select it and click Start. Now, let's start working with automated machine learning. Go to Authoring and then Automated ML. Let's create a new automated ML job. If this is your first time creating a new automated ML job, you'll be dropped on the training method page. Select Train Automatically, then click Start Configuring Job. Give your job a name. You can use the default one if you want. And then select an existing experiment name. Use the default experiment. You can leave the description, tags, name, and value blank. Then click Next. The dataset we'll use concerns a bank's marketing efforts. It contains data on the potential customers, how they were advertised to, and whether they used the bank's products. We want to make a classification model to predict if a given potential customer will use the bank's products. In Task Type and Data, select Classification. Under Select Data, click Create. We'll give our data asset a name. I'll call it Bank Data-2. And make sure that the data type is tabular. Then click Next. You may be asked here to select a destination storage type. If so, select the default data store that was automatically set up during your workspace creation. Workspace blob store, all lowercase, no spaces. You upload your data file to this location to make it available to your workspace. On the data source page, select From Web, and then click Next. Our dataset is available at this public URL. Feel free to pause the video here and copy it if needed. Then click Next. Here, we see a preview of our data, including the column titles and the values in each row here. Click Next. Here, scroll down and deselect Day of Week, since the day of the week probably won't have an effect on the outcome. Then click Next. Briefly review the settings, then click Create. Now, going back to the Automated ML job submission page, click Refresh if needed to make your new dataset appear. Select it, and then click Next. Under Task Settings, make sure to set Y string as the target column. This column indicates whether the client did business with the bank. Under Validate and Test, choose Validation Type, K-fold cross-validation, and select 2 cross-validations. Then click Next. You may also want to review additional configuration settings and make sure that the primary metric is AUC weighted and that you're using all supported models and that you are explaining the best model. Click Next. Under Compute Type, select Compute Instance, and then select the compute instance that you made sure was running at the beginning of this video. Then click Next. You can review the settings here, and when ready, click Submit Training Job to run the experiment. Once your experiment is running, feel free to get up and get some coffee because training may take a while. Let's summarize what we've done thus far. In this activity, you learned how to create a dataset in Azure ML Studio and create an automated ML task. Go on to Part 2 to see the results. What if you could train multiple machine learning models on your data, compare their performance, and choose the best one, all automatically? That's the power of automated machine learning. In the last video, you learned how to create a dataset in Azure ML Studio and create an automated ML task. In this video, we'll show you how to navigate model comparisons, generate detailed explanations, and uncover the insights that drive your model's predictions. Let's dive in and see how automated ML can revolutionize your workflow. Let's go to Azure ML Studio at ml.azure.com and enter our workspace. We will sign in if prompted, then click on our workspace to enter it, and then click on Automated ML under the Authoring section. One major benefit of using automated machine learning is that multiple types of models are trained automatically on your data, allowing you to compare them and choose the best one. Let's look at the completed job from the last video. This is the job completed from the last video. It has a different name, but all the same parameters. Click on it to enter the job. Navigate to the Models plus Child Jobs tab here and click on it. Here, we see all the different algorithms or models tested on our data. The models are ordered by scoring metric, which in our case was AUC weighted. Select the algorithm name of a completed model to see its performance details. I will click this one here since it has the best AUC weighted score. You can go to the Overview and Model sections here to explore the performance details. We see that training took 1 minute and 1.997 seconds. We can also generate model explanations on demand. The Model Explanations dashboard, that's part of the Explanations or Preview tab, summarizes these explanations. My explanations have already been generated, but to generate model explanations, click on Explain Model here, and then select Compute Instance from the drop-down menu, and then select your compute instance, and then click Create. Note that this will take 2 to 5 minutes to complete. I'm going to click Cancel since I've already created my model explanations and explain them here to you. Let's expand the left pane. Make sure you've selected the row with raw features. Now close the pane and select the Aggregate Feature Importance tab. This chart shows which data features influenced the predictions of the selected model. In this example, duration appears to have the most influence on the predictions of this model, suggesting that duration is the most important feature to explain the outcome. And that's it. In this activity, you learned how to navigate model comparisons, generate detailed explanations, and uncover insights from the results of an automated ML task. Automated training is a very powerful tool that can help you make better ML models quickly. It'll help you save time, letting you focus less on technical implementation and more on machine learning strategy. Now it's your turn. Choose another dataset and use automated ML to train models on it. See how the results compare to your manual attempts to train a model on the data and how much time you saved using automated ML.
Have you ever been frustrated by unexpected performance issues in your machine learning models? Knowing how to troubleshoot these problems efficiently can be the difference between smooth operation and costly downtime. Let's dive into a high-level summary of how to effectively troubleshoot Azure AI ML workflows to keep your models both reliable and accurate. By the end of this video, you'll be able to identify common challenges in Azure AI ML workflows. You'll be able to apply best practices for troubleshooting these challenges. Finally, you'll be able to discuss real-world examples of troubleshooting strategies that maintain workflow stability and performance. Troubleshooting Azure AI ML workflows is all about being proactive, systematic, and well-prepared. In a typical production environment, machine learning models and workflows often face challenges such as model drift, data inconsistencies, integration failure, and scalability issues. These problems can lead to reduced model accuracy, system downtime, or degraded performance. The key to effectively troubleshooting these workflows is to monitor critical metrics, diagnose root causes, and implement timely remediation actions. Automated alerts, proactive monitoring, and regular model retraining are crucial parts of a well-maintained workflow that helps prevent major issues before they escalate. There are several common issues you may need to address. First, model drift. Model drift occurs when the statistical properties of the input data change over time, leading to decreased model accuracy. For instance, if a model is used to predict customer churn and is no longer performing well, it may be because customer behavior has changed. The solution is to detect drift early and automatically retrain the model using the latest data. Set up automated monitoring using Azure Monitor to track key performance metrics like accuracy and precision. If a drop in accuracy is detected, trigger a retraining job using Azure Machine Learning to ensure that the model adapts to the new data distribution. Next, let's talk about data quality issues. Inconsistent or poor data quality can significantly impact model performance. Missing values, incorrect formats, or data that falls outside of expected ranges can all lead to errors or biases in predictions. Use Azure Data Factory to automate data validation and data preprocessing steps. Implement checks to identify and resolve missing or inconsistent data before it is fed into the machine learning model, ensuring that only high-quality data is used. Next, let's discuss integration failures. Machine learning workflows often depend on multiple components that need to work together seamlessly, such as data ingestion, model inference, and result serving. Integration failures can occur when one of these components fails or if there's a mismatch, for example, between their various interfaces. How do we fix this? Implement integration testing using Azure DevOps to automatically validate the compatibility between different components of the workflow, especially whenever changes are made. Regular testing helps ensure that the workflow continues to function as expected. Next, let's discuss scalability challenges. As workloads increase, maintaining the scalability of machine learning workflows becomes crucial. Inefficient infrastructure or inadequate resource allocation can lead to bottlenecks, resulting in longer response times and reduced throughput. To fix this, we deploy Azure Kubernetes Service, or AKS, to manage and scale machine learning workflows. AKS allows you to automatically scale resources up or down based on demand, ensuring that the system remains responsive even during those peak times of traffic. These best practices can help you troubleshoot Azure AI ML workflows. Next, let's discuss monitoring key metrics continuously. Use Azure Monitor to track important metrics, such as latency, accuracy, and error rates in real time. Monitoring these metrics allows you to identify and address issues before they impact model performance. It also allows you to automate the remediation process wherever possible to reduce downtime. For instance, automate the retraining of models if performance metrics fall below set acceptable thresholds. Incorporate continuous integration and testing practices to identify compatibility issues early. This ensures that changes do not disrupt existing workflows. You also need to maintain data quality. Implement data validation checks at each stage of the workflow to prevent issues caused by poor quality data. Use automated tools to clean and pre-process data before it enters the pipeline. Imagine, for example, a healthcare AI model that predicts patient outcomes based on incoming medical data. Over time, the model's predictions become less reliable due to changes in the types of patients being treated. By using Azure Monitor to track the model's accuracy and Azure Machine Learning to automate the retraining process, the healthcare provider can keep the model updated and accurate. Additionally, Azure Data Factory is used to validate incoming data for consistency, ensuring that poor quality data will not affect the model's predictions. In this video, you learned that troubleshooting Azure AI ML workflows requires a combination of proactive monitoring, systematic diagnostics, and automated remediation action. By following best practices such as continuous monitoring, regular retraining, and maintaining data quality, you can ensure that your machine learning models perform optimally in a production environment. Effective troubleshooting not only improves model performance, but also enhances the overall reliability and scalability of AI ML workflows. Reflect on the strategies discussed in this summary and think about how they can be applied to your own Azure AI ML workflows. Are there areas where you could enhance monitoring or perhaps automate remediation? Practice implementing these strategies to strengthen your troubleshooting capabilities and maintain high-performing machine learning models.
There was a specific use case that we had with the client, my team and I, where we were looking at comparing different healthcare benefits and a variety of different health-related opportunities and content in order to surface whether it's information or decision points. So the idea for us was simple. We wanted to analyze plan details. We wanted to predict out-of-pocket costs based off of that specific plan. And we wanted to recommend what the best option was based on an employee's preferences or their needs, or even connecting to a system of record that would enable us to understand who that employee was. So, again, for us on paper, it sounded like a win. It was a great opportunity, a great use case, and it was streamlining, which is a complex process that takes a lot of man and woman hours to make it easier for employees to make informed decisions, right? Amongst all the craziness of looking at one document versus another. And technically, when we started developing this AI use case and opportunity, the model worked. It met a general standard of accuracy threshold that we use to evaluate systems. However, as we started to look closer, it became clear that good enough and the way in which we measured kind of previous use cases wasn't going to cut it with this particular circumstance. For us, we leveraged Azure Data Lake for storage and managing the amounts of data that we needed. And we went through the actual fine-tuning of the LLM for the data and added some parameters upfront for chunking the data. But in healthcare, even a small inaccuracy could lead to serious consequences. Imagine for a second an employee selecting a plan that doesn't cover critical medical treatments or being blindsided by unexpected costs. These aren't just minor inconveniences. These are life-altering mistakes, and it's a big deal for a lot of people, for everyone, to be frank. And that's when we realized here that the stakes here were too high to rely on not just a standard accuracy threshold, but really the way in which we thought about what it means to parse out data, do chunking, look at the LLM to fine-tune the LLM to our specific parameters. Again, fine-tuning the model to improve precision in critical areas like predicting high-cost scenarios or gaps in coverage wasn't going to be sufficient for us. And we knew that because we tried it. We went through kind of our list of things that we can do in order to improve model predictability. The best we got it to was about approximately 88%. And so the lesson is for us, not all use cases are created equal. And there are certain use cases that are high stakes or high leverage that require not just a critical lens, but require us to really think through, does it make sense to develop this? Does it make sense for us to execute and release it out to a large employee population, particularly when it's dealing with people's personal health? And so, that transparency that is most critical in ensuring that there's a human safety net in place as we're thinking through these use cases. And ultimately, there are some where we can go to that 65% threshold or that 75% threshold or even that 85% threshold. But for use cases that are highly sensitive, in this particular case, like healthcare, it simply doesn't work. And the technology for us and what we have available at this point wasn't available for us to leverage.
Imagine you've just deployed your machine learning model and it's performing great. Accurate predictions, efficient processing, and everything seems perfect. But suddenly, there's a data breach and sensitive information gets exposed. All the progress you've made is at risk, all because of one key oversight: securing your deployment environment. In this video, you'll learn how to prevent this type of oversight from happening, and by the end of this video, you will be able to describe risks associated with deploying machine learning models in unsecured environments. You'll be able to identify the key principles of data security and their importance in Azure ML deployments. You'll also be able to outline best practices to safeguard machine learning models from potential threats. Deploying machine learning models involves more than just training and optimizing them for accuracy. One of the most critical aspects, often overlooked, is ensuring that the deployment environment is secure. Failing to secure your environment can have serious ramifications, including data breaches, legal issues, and reputational damage. Securing your deployment involves three key areas: protecting data at rest, securing data in transit, and managing access control. When your model is deployed, it interacts with stored data, otherwise known as data at rest. Whether it's the model itself, the datasets used for retraining, or logs perhaps from user interactions. Keeping data at rest secure involves encrypting it using tools like Azure Storage Encryption. Azure provides automatic encryption, ensuring that sensitive data is protected from unauthorized access, even if someone gains access to the storage account. Next, let's discuss data in transit. Data in transit is the data being moved between users, applications, and storage systems. Without proper encryption, this data can be intercepted by malicious actors. Azure provides options like TLS, or Transport Layer Security, to ensure that all communications remain secure. It's crucial to use TLS to safeguard sensitive information, particularly when making API calls or using data streaming in machine learning workflows. Next, let's discuss access control. One of the most vulnerable aspects of machine learning deployments is the access control mechanism. Improperly managed access can lead to unauthorized users interacting with the model or gaining access to sensitive data. Azure Role-Based Access Control, or RBAC, allows you to specify who has access to what resources. By restricting access to only those who need it and enforcing the principle of least privilege, you can significantly reduce the chances of a security incident. Consider, for example, a healthcare provider deploying a patient diagnostic model in Azure. Initially, they did not fully secure the deployment environment, which led to an incident where sensitive patient data was exposed to unauthorized users. This breach could have been avoided by implementing robust access control and encrypting sensitive data both at rest and in transit. After learning from this mistake, the healthcare provider updated their deployment by integrating Azure Private Link to prevent exposure to the public internet. They also enforced stricter RBAC, or role-based access control policies, ensuring all data interactions remained private and secure. So, how can you protect these key areas? Here are 4 best practices for securing Azure deployments. First, encrypt everything. Encrypt both data at rest and data in transit. Azure provides built-in encryption options that should always be utilized. Second, use private endpoints. Avoid public exposure by using Azure Private Link, which limits the network traffic to internal systems only. Third, use role-based access control, or RBAC. Restrict access to resources based on user roles. Ensure that only necessary individuals have access to the deployment and associated data. Finally, monitor continuously. Utilize Azure Security Center to continuously monitor for potential vulnerabilities and threats. Regularly audit access logs and security policies to identify and mitigate any risks. In this video, you learned that securing your deployment environment is not just a best practice, but instead an absolute necessity. Failing to secure your environment can put sensitive data at risk, damage your reputation, or potentially lead to severe legal ramifications. By understanding the risks and following best practices for data security, you can ensure that your Azure Machine Learning models are safeguarded against potential threats. Remember, your model is only as strong as the environment in which it's deployed, so make security a top priority. Take a moment to review your current deployment environment. Are you taking all the necessary steps to secure your model, your data, and your endpoints? Identify, if you would, one area where you can enhance your security measures today and put it into action. You're ready to launch your latest machine learning model into production. But what if, hidden in the data flow, there's a shift that could derail everything? In this video, we'll uncover common deployment challenges and solutions to keep your models performing seamlessly in dynamic environments. By the end of this video, you'll be able to identify potential issues that may arise during a deployment of a machine learning model. You'll be able to describe basic strategies to address common deployment challenges, and you'll apply critical thinking to anticipate and prevent problems in future deployments. Deploying machine learning models is exciting, but it also comes with a share of potential issues. Let's look at one common example of a potential issue, along with a simple solution to address it. This example is data drift. Data drift occurs when the data your model receives in production starts to differ significantly from the data on which the model was trained. This can lead to gradual decline in model accuracy and affect the quality of the ultimate prediction. Data drift is one of the most common challenges faced during real-world deployments, especially in dynamic environments where the data evolves over time. A possible solution is monitoring and retraining. To address data drift, it's essential to implement continuous monitoring of the model's performance. Azure Machine Learning provides tools to detect data drift by comparing real-time input data with the original training data. Once data drift is detected, it's crucial to retrain the model using updated data that reflects the current environment. By setting up automated retraining pipelines, you can ensure that your model stays relevant and accurate. Consider, for example, an e-commerce platform that uses a recommendation model to suggest products to users. Initially, the model works well, but as customer behavior evolves due to seasonal trends or new product launches, the recommendations become less effective. By implementing data drift, monitoring, and regularly retraining the model, the platform ensures that the recommendations remain accurate and useful for customers, maintaining user engagement and ultimately driving satisfaction. In this video, you explored key deployment challenges, such as data drift, that can impact the performance of machine learning models in a production environment. We discussed how monitoring and retraining strategies help address these issues, ensuring that models stay accurate, relevant over time. Using real-world examples like an e-commerce recommendation system, you saw how proactive management can maintain model effectiveness as data evolves. Reflect on the potential issues that could impact your own machine learning projects in deployment. Start by identifying areas where you might face challenges like data drift and think through ways to monitor and address these proactively. Taking these steps will help you deploy models that remain robust and responsive in dynamic environments.
Responsible AI is a central part in the way in which we should be thinking about in terms of when we're operating in our day-to-day, when we're in strategic meetings, or when we're just considering what we're going to build, right? So an example of why it's so important is there was a time where my team and I were tasked with automating employee performance evaluations. And the aim was really to categorize and bucket employees into successful or unsuccessful categories. On paper, it sounded like an incredible idea, an opportunity to improve consistency and efficiency in a much needed area, right? And frankly, something that AI in this particular case seemed perfect for. But as we started evaluating the project, I asked my team to pause and consider an important question. And that question was, just because we can, does it mean we should? And as we dove deeper, several challenges became clear. First, the data that we were working on included a ton of subjective elements. So things like peer reviews, disparities in opportunities, and other factors that could lead to biased outcomes. And if we weren't careful, the AI could unintentionally reinforce those biases, which would result in unfair assessments for our people. Beyond that, performance evaluations are inherently personal. So they require us to have a lot of empathy, a lot of nuance, and a lot of context for AI, because these are decisions that folks are making based on, if they're going to be promoted, there may be something highly sensitive in the subject matter itself. So for us, again, returning back to that single point, that question, just because we can doesn't mean we should. It became obvious that removing the human element from that would risk eroding trust and morals among employees. On top of that, there were broader concerns, including the potential legal risks of fully automating a system or a use case around this. And if you follow a lot of the legal landscape with respect to AI, much of the legal documentation and legislation we're seeing is in fact impacting how we're making decisions with our people. So we did explore ways to address these concerns. For example, we considered running a bias audit to identify and correct unfair patterns in the data. Primarily, we leveraged that through Azure. We also looked at human in the loop components, right? So to oversee and to validate AI's recommendations, we would have someone there every step of the way. But even with those measures, or these measures rather, we realized we couldn't guarantee fairness or prevent harm or equal opportunity and outcome. Ultimately, we brought our concerns to the leadership team, and together we decided not to move forward with this project. And it wasn't an easy choice, considering that there was a lot of leadership visibility on something like this, but it was the responsible one. And the main takeaway from this is truly, even if you can, that doesn't necessarily mean that you should, especially when it comes to this central idea of responsible AI. And just because a solution is technically feasible doesn't mean that it's the right path to take if it's going to have a significant impact on people.
Have you ever developed a high-performing model only to see it struggle when deployed in the real world? Without seamless system integration, even the best models can falter, facing issues from data bottlenecks to security vulnerabilities. By the end of this video, you will be able to explain the importance of system integration, identify key components of effective integration, and discuss business value through integrated systems. The motivation behind integrating your machine learning solutions into a secure system architecture is driven by the need for resilience, scalability, and efficiency. When different components of your machine learning deployment, like data pipelines, models, APIs, and security mechanisms, are well integrated, you get a streamlined and robust system that can handle both expected and unexpected challenges. Consider, for example, a scenario where a company has successfully developed a fraud detection model. It's not enough for the model to perform well in a development environment. For the model to be impactful, it must be seamlessly integrated into the broader infrastructure of the business, including data sources, decision-making workflows, and security systems. Without proper system integration, the value of that machine learning model can quickly diminish due to inefficiencies or security vulnerabilities. Here are the main components of effective system integration. First, Data flow and accessibility. Proper system integration ensures that data flows smoothly from the point of collection to the model training and prediction. This means setting up robust data pipelines that are both secure and reliable. Data should be accessible to your models without exposing sensitive information, and integration should include mechanisms like data encryption, API management, and access control. Next, scalable infrastructure. A well-integrated system enables scalability. As your data grows or model demand increases, the infrastructure must be able to scale seamlessly. This can be accomplished through Azure Autoscale, Kubernetes for containerized deployments, or even serverless architectures. Integrating these components allows your machine learning models to scale without manual intervention or the risk of failure. Next, security measures. Integration should incorporate multi-layered security measures. As discussed in earlier lessons, combining solutions like API gateways, OAuth, NSGs, and RBAC can help secure different parts of your deployment. By integrating these solutions, the system is better prepared to handle a variety of threats, from unauthorized access attempts to full-scale data breaches. Imagine, for example, an e-commerce company aiming to deploy a recommendation engine to personalize user experiences. Effective integration would involve connecting the recommendation model to user activity data streams, sales data, and inventory management systems. Integration would also involve securing the model endpoint using private links and controlling access using role-based permissions. With a properly integrated system, recommendations are updated in real time, ensuring that customers receive relevant product suggestions while keeping the underlying data secure. Integration is not just about connecting components. It's about making them work cohesively. By integrating your machine learning deployments into a well-orchestrated system, you ensure consistency, reduce latency, and minimize manual intervention. More importantly, you create a resilient architecture capable of adapting to changes in data, user needs, and business goals. In this video, you learn the importance of integrating machine learning models into a secure and cohesive system for long-term impact. System integration provides resilience, scalability, and efficiency, ensuring that data flows smoothly, infrastructure scales with demand, and security is built into each and every layer. By integrating data pipelines, models, APIs, and security mechanisms, you create a well-orchestrated system capable of adapting to evolving data and business needs, ultimately increasing the value of your machine learning deployments. Reflect, if you will, on your own machine learning projects. Consider how data, security, and infrastructure components connect, and try to identify any gaps in integration. Think about implementing strategies such as robust data pipelines, scalable infrastructure, and layered security to achieve seamless, secure integration. Taking these steps will transform your models from standalone assets to vital parts of a larger, more impactful system. Think back for a moment to where you started. Perhaps machine learning felt overly complex, or deploying models seemed so far out of reach. Well, now you've built the skills to confidently deploy, scale, and secure ML models that can transform real-world applications. As we conclude, let's reflect on how each piece of this journey has empowered you to tackle these challenges head-on. In this video, you'll review the most important takeaways from this course. Starting with machine learning fundamentals. We began by building a solid foundation in machine learning concepts, exploring supervised and unsupervised learning, and understanding model training, validation, and evaluation. This foundation is essential for understanding how models operate and how to optimize their performance in various settings. Next, we explored deployment techniques. Throughout the course, we discussed different deployment strategies for machine learning models, including containerization with Docker, deployment with Azure ML, and the importance of automating workflows using CI/CD pipelines. These strategies ensure that your models are ready for real-world use and can be managed effectively. We also discussed security considerations. One of the most important topics we covered was how to secure your machine learning environments. We learned about using tools like OAuth, network security groups, role-based access control, or RBAC, and Azure Private Link to protect both the data and the models. Implementing these security measures is crucial to maintaining trust and reliability in your deployments. We next talked about scalability and systems integration. As your machine learning projects grow, scalability and integration become ever more critical. We explored how Azure Autoscale, Kubernetes, and serverless architectures allow your systems to grow alongside demand without compromising performance. Proper integration of data flows, APIs, and security mechanisms ensures your machine learning deployment becomes part of a cohesive, resilient infrastructure. We then talked through real-world applications. Throughout the modules, we looked at these examples like fraud detection, personalized recommendation, and predictive maintenance to illustrate how machine learning can solve real-world business problems. These examples showed how integrating models with business operations can lead to impactful outcomes. The ultimate goal of this course was to equip you with the skills and knowledge to not only develop machine learning models, but also deploy them securely, scale them effectively, and integrate them into broader systems to solve real-world challenges. By understanding the full life cycle, from data collection to deployment and maintenance, you are now prepared to tackle end-to-end machine learning projects that bring value to your organization. But remember, your journey doesn't end here. Machine learning is a rapidly evolving field, and the skills you've learned in this course are just the beginning. Stay curious, keep experimenting, and apply these concepts to real-world projects. The more you practice, the more you iterate, the more proficient you'll ultimately become. The world needs machine learning solutions that are ethical, scalable, and impactful, and you now have the power to create them. As you move forward, think about how you can apply what you've learned to your own projects. What are the next steps you can take to improve your machine learning workflows? How can you contribute to building secure and effective systems? I encourage you to stay engaged with the community, continue learning, and always look for opportunities to innovate. Congratulations once again, and I wish you the best in your machine learning journey. You've done it. You've completed an entire course on machine learning, and that is no small feat. Take a moment now to appreciate how far you've come since you started. Completing this course is a major achievement. Throughout the modules, you've learned not only the theoretical concepts behind machine learning, but also gained hands-on experience in deploying, scaling, and securing models in real-world environments. You've tackled challenges head-on and come out the other side with a set of valuable skills that will serve you well in your career. Here's a quick recap of what you've learned. First, foundational knowledge. From understanding basic concepts like supervised and unsupervised learning to diving into more advanced techniques like hyperparameter tuning and model validation, you've built a solid foundation in machine learning. This knowledge will be crucial as you apply these methods to solve real-world problems. Hands-on experience. You've had the opportunity to work with data, train models, and deploy them into potential production environments. You've learned how to integrate machine learning models using tools like Docker, Flask, and Azure, and how to ensure that these models are both scalable and secure. Practical solutions to real problems. The assignments and projects throughout this course were designed to mirror real-world challenges. Whether it was creating a recommendation system or building a fraud detection model, you've learned how to leverage machine learning to create impactful solutions. Remember, this is just the beginning. The skills you've developed here will serve as a stepping stone for further learning and more challenging projects. Machine learning is, of course, a rapidly evolving field, and there's always more to learn. I encourage you to stay curious, read research papers, explore new tools, and most importantly, continue building. So, what are your next steps in this journey? Apply your skills. Look for opportunities to use your machine learning knowledge in real projects, whether at work, in your community, or through personal endeavors. Keep learning. There are countless resources available, books, online courses, research papers, to help you take your skills to the next level. Consider perhaps specializing in a specific area like natural language processing or computer vision if you found it particularly interesting. Engage with the community. The machine learning community is rich with knowledge and collaboration opportunities. Engage with peers, participate in online forums, or join a local meeting group. Sharing your knowledge and learning from others will accelerate your growth. Congratulations once again on completing the course. You've put in the time, effort, and dedication to master complex topics and gain hands-on experience. Now it's time to take what you've learned and make an impact. Whether you apply these skills in your current job, embark on new projects, or just continue learning, you now have a strong foundation upon which to build. We're excited to see where this journey takes you. Keep pushing forward, and remember, the world needs innovators just like you.